Okay, hello everyone. Sorry, I lost my chat for a moment. So, welcome to the second open session of this conference. So, the second and the last one. And so today we are delighted to have three speakers. So, the first will be Ronald de Wolf on two open problems in quantum communication complexity. Okay, so the second speaker will be William Kretschmer, so on learning quantum states, so an open problem. And the last one, but not least one, is Marc-Oliver Renou, and the topic to be announced yet. Okay, so if you have any questions so to the speaker, so feel free to post them in question and answers or just write in the chat. And so I think that's it. And so without further ado, I introduce our first speaker, Ronald de Wolf from CWI. And so Ronald, you can now speak.
Okay, thanks, Alexander. Let me try to share my slides. Okay, I hope you see my slides, Alexander. Can you verify?
Yes, everything is fine. So slides are so I can see you. So
this is about two open problems in quantum communication complexity. Let me start by spending one slide on what is quantum communication complexity. So communication complexity in general, no matter if it's classical or quantum, you should really think of it as a very basic bare bones model of distributed computing, where you really only care about the amount of communication that goes between the different nodes in the network, and you don't care about the cost of local computation. Local computation is essentially free here. So let's take the simplest case, a network of only two parties, Alice and Bob. So Alice receives some input X from some domain capital X. Bob receives some input Y from some domain capital Y. Think of X and Y as n-bit strings, for instance. And now they jointly want to compute some function. Think of it as a Boolean function that depends on both X and Y. Right, so a simple example would be deciding whether X is equal to Y or not, or maybe deciding whether let's say if X and Y are, let's say, n-bit strings, whether they agree in a certain number of positions, things like that. And the goal here is to minimize the one resource that we care about, which is the amount of communication going back and forth between Alice and Bob. And you can study classical communication complexity where the communication is classical, or you can study quantum. And in general, protocols look like this. Let's say that Alice starts the communication. So she looks at her input X, sends a message to Bob. Bob looks at that message, also looks at his input Y, sends back another message. Alice returns yet a third message, and so on. And this goes on for however many rounds they need. And at the end of the day, let's say that Bob is required to output the output value Z, and then we would like this Z to be equal to the function value fx, y, either with probability 1 or let's say with probability at least 2/3. And the thing I want to emphasize about this model is that if you compare quantum and classical communication complexity, then this is a model that actually proves exponential quantum classical separations, and it happens in a physically realistic model. And I want to contrast this with two different separations. One, of course, is Shor's algorithm, probably still kind of the most famous quantum algorithm that we have. And this probably establishes an exponential improvement in time complexity for solving the factoring problem. So it's probably exponential, but we don't know how to prove this because proving that factoring is hard classically would imply P different from MP, and we have no clue how to do that. Right, so Shor's algorithm is probably exponential, but we don't know how to prove it. And on the other hand, in the case of query algorithms, let's say things like Simon's problem, you can prove exponential separations, but it happens in a somewhat unrealistic model because there's sort of the input is given in the black box, and at least my students always complain about this model. They don't think it's realistic. And as soon as you start opening the black box, the whole story changes. Right, so communication complexity has two of these advantages. It provably gives you exponential separations, and it does so in a realistic model. And I've spent a lot of my, let's say, research time on communication complexity. And what I would like to do in this little talk is to present you with two problems that I worked on for more than 20 years and made very little progress on. And the first one is the problem of how much entanglement can help in this model. So when I say entanglement, I mean sort of a pre-shared resource. Let's say that Alice and Bob share a bunch of EPR pairs at the start of the protocol, and they're not charged for that. It's free quantum correlation, so to speak. And the question is, how much can this reduce communication complexity? In general, even classically, such shared resources can reduce communication complexity at least somewhat. So in the classical case, the sort of the starting point is shared randomness. Let's say that Alice and Bob have access to the same source of random coin flips. And we know that classically shared randomness can reduce communication complexity at least somewhat. Like if you look at the equality function, for instance, let's say Alice and Bob each get an n-bit string, x and y, and they want to decide whether these two strings are equal or not. Without shared resources, the communication complexity is essentially log n. With shared randomness, it drops down to constant, order 1. So that's an additive reduction of log n bits of communications thanks to the shared resource of shared randomness. And Newman's theorem, that's a famous theorem in communication complexity, says that this is essentially optimal. Whenever you have a protocol that uses, let's say, C classical bits of communication and an enormous amount of shared randomness, you can always kind of reduce that amount of shared randomness to logarithmic in n. And in particular, this means that if you have a protocol that uses C bits of communication and an enormous amount of shared randomness, you can actually convert that into a protocol that uses C plus log n bits of communication and no shared randomness at the start. Right? The idea is just that Alice would flip the log n coin flips that are needed and send them along to Bob with the first message. So you can very cheaply get rid of this shared randomness. And the question I'm asking on this slide is whether the same is true for entanglement. And of course, shared entanglement is a much more rich shared resource than shared randomness. And it can also reduce communication in several ways. The first way is to use super dense coding, right? Like if you consider a protocol, let's say that our f is a random function on n-bit strings, then you can show that if you don't have anything shared, no shared entanglement, then Alice and Bob need to exchange roughly n qubits of communication. So for a random function, the trivial protocol is essentially optimal. But if they start out by sharing entanglements, then they can use super dense coding and use 1 qubit to send 2 classical bits from Alice to Bob, thereby reducing the communication by a factor of 2. Super dense coding is pretty nice, but a factor of 2 is not very much. And the other way in which shared entanglement can reduce communication is just to use it as shared randomness, right? If you and I share an EPR pair and we both measure it in a computational basis, we get a shared random coin flip, right? So the additive log n that you get for equality from shared randomness, you can also get it from shared entanglement. And these two effects are basically all we know about how entanglement can reduce communication complexity. And my question is, are there more powerful ways in which entanglement helps? Or if not, can we prove something like a Newman's theorem for entanglement? Right, and here's one formulation that this Newman's theorem might take, right? I don't dare to phrase this as a conjecture, but something like this might be true. Let's say there is a protocol for a function f, and it uses q qubits of communication and r entangled qubits. R could be huge. Then there's another protocol that uses q plus log n qubits and no prior entanglement. Right, this would be sort of a quantum analog of Newman's theorem, with the quantum shared resource being entanglement instead of public randomness. And this is pretty hard to prove. Like I know some people try it. The obvious things don't really work. And all I have in my 20 years of work is the following unpublished little result. It says the following: if the f that you're talking about, the function you want to compute, has a special property called the direct sum property, and in fact, almost all, but not all functions satisfy that property, then you can get rid of the entanglement at the expense of a factor of log r increase of the communication. And you might think of log r as a big price to pay, but if you're sort of thinking about reasonable resources, then you don't want to allow more than, let's say, polynomial in n many EPR pairs at the start. And in that case, the log r factor is just a log n factor. right? So protocols for functions that satisfy direct sum that use a polynomial number of EPR pairs at the start, you can actually get rid of the entanglement at the expense of only a logarithmic factor increase in the communication. And I don't have anything else to show about this open problem, but I think it's interesting, and it kind of ties into a much bigger story, which is, I think, one of the key questions of quantum information in general. How much does entanglement help us? This was my first open question. Should I pause for questions, Alexander? Or just move on to the second?
There are no questions yet, so you can move on. And so there are questions.
Okay, I'm not seeing the chat, so if you see something in the chat, please interrupt me. Mm-hmm. Okay, so this was my first problem. How much does shared entanglement help in reducing communication? And my second one kind of interfaces with query complexity, or rather it's inspired by results from query complexity. And this asks whether there can be exponential quantum savings in communication if you talk about total functions. And the starting point here is an analogous result which has long been known for quantum query complexity. Namely, if you look at all total functions on n bits, and by total I mean that the function is defined on every possible n-bit string, so there's no promise on the form that the input can take, then the classical deterministic query complexity and quantum bounded error complexity are polynomially close. There cannot be exponential separations between them. They are at most some power apart. And here's a very simple proof of this. First, so let Q of f be the bounded error quantum query complexity. Then you can show that this is always lower bounded by the square root of some measure called the block sensitivity of f. And this item number 1 is essentially just the Grover lower bounds, slightly generalized. And you can also show that classical deterministic complexity is upper bounded by a polynomial in the same quantity block sensitivity. And if you put these two things together, you get that the quantum bounded error query complexity is at most a 6th power smaller than the classical deterministic query complexity. So they're always kind of close. There are no exponential separations. Of course, there are polynomial separations, for instance, for Grover, but there cannot be exponential separations in query complexity for any total function. And my question on this slide here is the same question for communication complexity. So let's say we have a total communication complexity problem. Alice gets n bits, Bob gets n bits, and the function outputs 1 bit. And the function is defined everywhere. So no matter what x and y are, f of x comma y is always defined. This is not a promise problem. And the question I'm asking is, can there be super polynomial separations for any total functions between quantum and classical communication complexity? And we have to be careful here about which model we're looking at exactly, because if you're looking at classical deterministic protocols, then we already know exponential gaps, even between classical deterministic and classical randomized protocols, for instance, for equality. For equality, the classical randomized complexity is log n, the deterministic complexity is n. So to make a fair comparison here, we should be comparing quantum bounded error protocols with classical bounded error protocols. Right, so the question is, can quantum communication complexity be exponentially smaller than randomized, or are they polynomially close? And actually anything in between would also be very interesting. I would be very happy to see some total function, with slightly super polynomial separation between quantum and classical communication complexity. And if this is not true, like if you could do something like what you can do for query complexity, then I think the key should be to find the right distributed version of block sensitivity so that you can mimic the query complexity proof that I put at the top of the slide, so that you find some sort of combinatorial or complexity measure, where on the one hand you can lower bound the quantum communication complexity by some polynomial in that measure, and on the other hand you can upper bound the classical complexity by some other polynomial in that same measure. And I don't know what that measure would be. And you can ask the same question also for one-way communication complexity, where Alice just sends one message to Bob. Maybe that's easier to analyze, but 20 years of work on my part have yielded nothing. So this was my second and last open question. Back to you, Alexander.
Okay, thank you, Ronald, for the presentation. I think there are two very, very clean open problems, so to think about. Okay, so I see no questions here, but I have maybe one question.
Yeah, please.
Very simple. maybe very simple that you can answer. For the first problem, so if you don't know how to measure entanglement, but say if you just have shared randomness and quantum communication, then can you show that you can reduce shared randomness?
Yeah, so the proof of Neumann's theorem applies. If I give you a quantum protocol that uses q qubits of communication and a massive amount of shared randomness, you can reduce that to a protocol that uses q qubits of communication and order log n shared randomness.
Okay.
It's a very simple sort of probabilistic argument, where you pick order n elements from this large bag of random strings, you fix those. This is going to preserve all the success probabilities essentially, and now your new protocol is just going to pick a random element from this small set of order n random strings. And this applies no matter whether the underlying protocol uses classical or quantum communication.
Okay, thank you. So I think there are no other questions, so we can thank Ronald now for very interesting talk.
I will stop sharing.
So if you have any questions, of course you can shoot sharing, and so we can of course ask any questions offline if you feel free. So now we can move to our second speaker. So our second speaker is William Hesmer. Okay, so hello William. So whenever you're ready to talk, then start sharing your screen and start talking.
Sure. Okay, hopefully I can. Can you see this?
Yes, everything is fine. Yes, thanks.
Okay, good. And by the way, I apologize in advance if I stumble over any of my words because it's extremely late here and I'm pretty tired, but I'll do my best. So as the title suggests, I'll be talking about one of my favorite open problems, which has to do with learning constant depth quantum states. And the funny thing about this problem is that I've discussed this problem a lot with other people. I'll mention it in passing, and a lot of other researchers will say in response, "Oh yeah, I've also been thinking about the same problem or something along the same lines." And this is despite the fact that I've never actually seen this problem written down explicitly anywhere. So my hope is that by presenting this here, it will perhaps inspire some discussion or get more people thinking about it, and maybe we can solve it. So without further ado, the setup is pretty simple. So we have some n-qubit quantum circuit, and the depth of this circuit, d, is some constant. So we can think of it as being like, in this case, 3, let's say. And this produces some quantum state psi. And the question is, basically, given a bunch of copies of these states psi, can you efficiently recover some description of this quantum state? And there's many different senses in which one could try to learn psi, right? There's pack learning, there's shadow tomography, but what I'm really asking about is essentially the strongest type of learning one could hope for, which is basically finding an explicit description in the form of a unitary transformation that actually approximately produces this state. And really, the main question here is whether you can do this in a time-efficient manner. So, for instance, if you saw Srinivasan's talk earlier in the conference, one of the things he mentioned is how in learning theory for quantum states, there have been a lot of positive results for information theoretic learning, so showing that we can learn things with low sample complexity, but we don't really have many positive examples of classes of quantum states that we can learn in a time-efficient manner. I think, some of the only examples are like stabilizer or near stabilizer states. And basically, I'm proposing this as one candidate that is worth exploring. Because in a certain sense, it looks like it should be very easy because of this constant depth property. And so for that's basically the whole setup of the problem. I'm just going to spend the rest of this time just talking about some observations about this problem. And one is that one thing that is easy to do is to find what you might call light cones. So what does that mean? So a light cone of some qubit, let's say this qubit that I've highlighted in red, is just some sequence of unitary gates that we can apply in reverse to the state psi, such that if we apply these unitary gates, then we'll set this qubit back to the all zero state. And so, for instance, if we just take this circuit that we started with and we take all these red starred gates and apply them backwards, then we will set this qubit to the all zero state. And okay, why is it easy to find these light cones? Well, because the depth of the circuit is d, which is some constant, and each gate acts on at most 2 qubits. The size of one of these light cones is at most 2 to the power of d, and since d is a constant, 2 to the d is constant, and you can basically just brute force over all of these in polynomial time in the number of qubits. So this like almost gives us a learning algorithm, because we can find out how to set one of the qubits to 0, and we can sort of repeat this for all of the qubits. And so you might imagine that by finding these sort of light cones for all of the qubits, we'd basically be done, because we would have found a unitary transformation that just sets all of the qubits to 0. Except the hard problem here is basically stitching these light cones together into a consistent manner. So the problem here is that these light cones need not be unique. There could be many different sequences of unitary gates that could set one of these qubits back to 0. And it's not obvious whether there's a nice way to efficiently put all these possible light cones together into some consistent global unitary that will take psi back to the all zero state. So that's sort of, as far as I know, why this problem might be hard. So despite that, there are at least a few cases where I believe this problem is easy. So one example, it turns out if the depth of the circuit is 2, then it's easy. And here, there's sort of a simple greedy algorithm, essentially the first thing you would try if you were trying to solve this problem. And you can basically just show that this naive strategy just works. A slightly less trivial example is if the architecture of the underlying constant depth circuit is one-dimensional. And what this means is that all of the qubits are arranged in a line, and all of the 2-qubit gates act only on pairs of adjacent qubits. And the reason why it turns out one can actually solve this problem efficiently in one dimension is that it turns out you can basically solve constraint satisfaction problems efficiently in one dimension. So if you've ever heard of like, the belief propagation algorithm, you can basically find all of the possible consistent light cones for each local qubit and then put them together into some global assignment. I think slightly more generally, this is something I haven't really verified, but I believe, you can also generalize this. So if you know the architecture in advance of the circuit, meaning you know where all the gates are located, and if that the graph corresponding to that circuit has bounded tree width, then I believe in that case, one could also solve this efficiently. And again, this is just because on graphs of bounded tree width, of which one-dimensional graphs are a special case, you can solve these sorts of constraint satisfaction problems efficiently to put these light cones together into a consistent fashion. But that's basically everything I know about this problem. If I had to take a guess, I could see that this problem could be hard in the worst case. I would not be too surprised if this were hard in the worst case, but I would be very surprised if this problem turned out to be hard on average. And here by on average, what I mean is you imagine, say, fixing some architecture, and then you just choose all of the gates to be Har-random unitaries. In that case, my guess would be that this problem should probably be easy. And my intuition there is that the light cones should probably essentially be unique when all of the gates are basically random. I can't prove that, but that's just my intuition. If you if you disagree or if you have any other ideas, I encourage you to email me, or perhaps we could even discuss it here at this conference. But yeah, that's basically everything I had to say. Also, if you want to hear more about my thoughts on this problem, you're more than welcome to email me. I could talk about this for hours probably, because I have spent a good amount of time talking about this. But with that, I think that's everything I have to say. So are there any questions?
Okay, thank you very much for your presentation. I think it's an interesting problem. And okay, I think we now have one question, but it's now for Renaud. I think it makes sense maybe to that I add this question to Renaud and then Renaud answers, and then we move to the question to William. I think it makes sense given our online question. So okay, so let's start with the question to Renaud. Okay, so Renaud, can you hear me?
I can. Is this the question in the chat by Anurag?
Yeah, the K in the chat. You can read it yourself.
I already answered it in the chat.
Oh, I see. I haven't seen it. Or maybe. Okay, good. Then there is another question to William, I guess. So the question for William is from Anurag and Shu. So the question is, would you be interested in any circuit that generates the raw states?
Yes, I think, right. So one way of saying that is like, do you care about proper learning or not? So yeah, from my perspective, it would still be interesting, even if you cannot recover the original constant depth circuit. If you can just find any efficient way to produce more copies of this state, that would be something that, as far as I know, we don't know how to do. So yeah, any partial results would be nice.
Okay, I think I just have one clarifying question for your thing that just your settings that you have just copies of the states that you just have in like unbounded amount of copies and then you can work with them, right?
Right. I mean, okay, presumably one would
Yes.
imagine it being like a polynomial number of copies. I suppose slightly more generally, you could even suppose you have like a unitary transformation that produces the state as a black box. But I think the simplest case to consider is you just have copies of the state.
I see. Okay, so
oh, and I should also mention, I guess this assumes like it's a pure state, I guess. Presumably for mixed states, it's even harder.
Okay,
can I ask a question to Alexander? Can I ask a question to William?
Of course you can, yes.
Is there a relation here with this QMA hard problem of K local density matrix consistency? Where you're given a bunch of overlapping descriptions of density matrices, and you want to see if you can stitch them together into one big n-qubit density matrix?
Perhaps, but what's interesting about this problem is that it is. So this is something I didn't mention, but it is definitely not QMA. Well, probably not QMA complete because it is in NP. Or at least it's reducible to NP. This sort of constraint satisfaction problem, you can verify the constraints without a quantum device. So
I see.
Yeah, it's not, yeah, and that's, I think, also intuitively why maybe this problem is easier, is that somehow, even though it involves quantum states, the hard aspect of it seems to be purely classical.
See, thanks.
Okay, yeah, see, Ronald, so let me get back to you. I think there is kind of misunderstanding. There was one question for you in the chat and another one in Q&A. I don't think that you answered the one in Q&A from Matthias Kerr.
I don't even see the Q&A, so maybe you can relay it to me.
Yeah, so I can read it. So it's one question. So thank you so much for presenting these two interesting problems, Professor De Wolf. I have a question about the potential separation between classical and quantum one-way communication complexity. So there's the question. If I remember correctly, Aronson's quantum Occam's razor has an application in bounding the separation between randomized classical and quantum one-way communication complexity. But the bound depends on the size of Bob's input. Do you think that learning theoretic result could help in attacking the communication complexity problem you propose?
It's an interesting question. I haven't really thought about it. I guess this would attack the one-way version of my second open problem. I guess the short answer is I don't know, but I'll think about it. Thanks for the question.
Okay, so I think that's an interesting idea.
Mm-hmm.
Okay, thank you very much. Okay, so things around. Okay, so there are no questions so much. So we can now, thank you, William, for your presentation again. So we can now move to our third and last speaker of today. So it's Marc-Olivier Renaud. Okay, so Marc-Olivier, when you are ready, so just please share your screen, turn on your camera and microphone and start speaking. So I just can't see you yet. Okay, so I can see you now.
Yes. Hi, everyone. Yeah, so I'm sorry, there were a misunderstanding. So I was not confirmed. I had to present an open problem today, but well, I have something clear in mind and I have found some slides, so I hope it will be clear for you also. So let me share my screen. Yes. So the problem I want to discuss today is something about generalization of quantum mechanics for correlation in networks and ways to understand them. So we all know standard Bell non-locality, in which we have a source which is shared between several parties, and the parties have input, obtain outputs, and obtain a probability distribution of the outputs knowing the inputs. And there are several explanations for this. So there are classical models where we have a local hidden variable. There are quantum models where we have quantum states and quantum measurements. And then this was generalized to, for instance, no signaling boxes, such as the peer box, in which the only constraint we put on the model is the no signaling hypothesis. So X cannot be known by C in the process of obtaining C, for instance. And this is somehow the most general model we can imagine in such a scenario. So this is something we do not observe in practice, in experiments, but this is something which could be, let's say, a priori could exist as a theory because it does not violate the no signaling hypothesis. So what I want to talk about now is how to do this in networks. So how to construct this most general and imaginable theory in networks. So in networks like this, we have now a new model for our correlation in which we have 3 independent sources, and the strategy of the party will be based on those sources. So for instance, Alice will just output A, which is a function of X, beta, and gamma. This is for a classical model. And then we can also imagine quantum models in which now we have quantum states, and A will be just a quantum measurement of rho beta and rho gamma according to X. And we can also imagine that those sources are no signaling box, but actually this is not the most general model we can imagine. And the question is, what is the most general model we can imagine? So this is what I want to explain now. So the way to define this most general model, so now I have resources R beta, R alpha, and R gamma, which are post-quantum, like from a post-quantum theory, and I want to make it as general as I can. And the only constraint I want to impose is this constraint of independence of the 3 sources. So the way one can do it, and it was done by several people, is to do it through device replication and causality. So what we say is we imagine that there is a strategy in some post-quantum theory, which is not known today, but which is based on some resources, R alpha, beta, and gamma, which creates a probability distribution P ABC. And we assume, but somehow we must assume this, the theory will always satisfy this. We assume that we can replicate those devices, R alpha, R beta, R gamma, into independent copies. So this R alpha, for instance, I can create two copies of it, one R alpha and one R alpha prime, which will be completely independent and which I can place in a new inflated network like this. And in this new inflated network, I have this R alpha, I have also a copy of R gamma, etc. They are all independent and they are connected to the same parties who perform the same measurements. So I should obtain in this new network a probability distribution over A, B, C, A prime, B prime, C prime. And so this is I start from a problem in which I have a P and I want to know if there is a theory I can imagine which can produce this P. And for this, I propose a test, which is to imagine by contradiction that there is a way to obtain this P and create this inflated network in which I should have a Q which should satisfy some constraints which are given by causality. So for instance, well, if I look at AB in this new network, you see that they see exactly the same environment as in this first network. So the marginal probability of AB should be the same in the two networks. So this is a first class of constraint. So I have this also. And I have a second class of constraint, which is a compatibility of Q with the network, the inflated network itself, which is, for instance, that here you see that A and B and A prime and B prime do not share any source in common. So this probability distribution should factorize like this. So those are some constraints. And I will say that P is feasible in this triangle network in some generalization of quantum mechanics, as soon as for all inflated network, all imaginable inflation. So here I have 6 parties because I did 2 copies of each sources, but I can do 3 copies and have 9 parties and go higher and higher like this. So it's a hierarchy. So P is feasible if for all inflation, there exists a probability distribution Q, which satisfies all the compatibility condition I can find with P and with the network itself coming from causality. So some marginal equality like this and some factorization equality like this. Okay, so this is what I wanted to present as a problem. And now the question behind is, well, how hard is it to characterize this whole set? So you see that here I am elaborating a characterization which is coming from a hierarchy because I have to take larger and larger inflation, and for each inflation I have a feasibility problem. But I would say that P is feasible only if this is valid for all inflation. And if I look at a fixed inflation, the problem is non-linear, right? Because I have some linear constraint, but I also have some quadratic constraints. A second open problem is to find the link between this definition and the generalized probability theory definition. And then maybe a last, which are given by those inflation, but which can only be found with infinite inflation. So which are not easy to find with a numerical algorithm, which would enumerate small inflation to find constraints. I think there exist constraints which are given by some sequences of infinite inflation, which cannot be understood with a computer, for which we need to do something analytical. So, well, I am done.
Okay, so thank you for your presentation, and So it's the last moment to ask questions to any of our speakers. Okay, so I think there is a follow-up question in chat to Ronald de Wolf. Okay, so Ronald, can you see it?
There is something there, but the person who writes the question says that I can ignore it. Let me just quickly read it. I think it's basically a comment on the earlier question. It's by Matthias Caro, who earlier asked a Q&A question.
Yes.
I don't think there's much for me to say here.
Okay, thank you.
Thanks anyway.
And, okay, so I think there are no other questions for today's open session. So I think that it's a very good thing that we have now all these open problems to think about. So in case if you are watching for open problems. And so I would like to thank again all three speakers of today's session. And okay, and then I think then we can just finish. So thank you very much for presenting, and thank you very much for attending and listening. Okay, goodbye.
Hi, welcome to this session for TQC. We are very pleased today to have Pablo tell us about this work about the XZZX surface code. Pablo, you may begin.
Thank you. Can you see the slides? Cool. All right. So thank you for all the organizers for putting together TQC. My name is Pablo, and I will talk today about the XZZX surface code, which is joint work with my awesome supervisors, David Tuckett, Ben Brown, Steve Bartlett, and Steve Lamia. And this was work done at the University of Sydney. I won't have time to go through all the results in this talk. So if you want to see, get more information about the XZZX surface code, you can check the extended talk and also check out the archive link. So the whole premise of the work that we did is based on a line of research that David Tuckett pursued in his PhD thesis. And it's to do with tailoring quantum error correction codes to the structure of the noise on physical qubits that we're using to build a quantum computer. It turns out that in a lot of physical qubits, the dominant noise type is dephasing. And a particularly interesting example are these Kerr-Cut qubits, which are highly biased. And what's more important is that people have designed gates which maintain the bias of the qubits. So in particular, we can retain the gains of exploiting the bias when using these tailored quantum error correction codes. So we abstract this bias noise and we make it into a toy model, which I'm going to present now. So here at the top, you can see a depolarizing channel where X, Y, and Z errors all occur with the same rate, little p on 3. And here's the noise model that we studied, where X, Y, and Z errors occur with probability px, py, pz, respectively. And we quantify the bias through this coefficient here, which is given by pz over px plus py. And you can see that if we increase the rate of z errors compared to x and y errors, we increase the bias as required. Two notable limits are a bias of infinity or purely dephasing noise, where only z errors are occurring, and on the other extreme, a bias of 1/2, where x, y, and z errors occur with the same rate. So the XZZX surface code is obtained from the normal CSS surface code, which you can see here on the screen, by applying a Hadamard gate to every other qubit, the ones highlighted in green here. So you can see that the X stabilizers go from all X to going to being X, Z, Z, X, and similarly all the Z stabilizers become X, Z, Z, X. So every single stabilizer in the new code is an X, Z, Z, X. And the reason we expect it to perform well against a noise model where Z errors are occurring very often is because now every single stabilizer in the new code can detect these Z errors because they anti-commute with the axis. So here are some of the results we collected. David Tuckett collected using maximum likelihood decoding. And what I'm presenting here is the threshold on the y-axis. And on the bottom, you can see the bias of the noise, the direction of the bias. So here will be purely Z dephasing. And here will be purely X errors and purely Y errors on that corner. And in the middle would be depolarizing. So it turns out that everywhere on this surface, the XZZX surface code matches the hashing bound, which is a bound on the quantum capacity of a channel. And it even appears to exceed it in some of these purely biased regions here in X and Z. If we compare it to the tailored CSS code, we see that in the direction that the normal CSS code, in the direction of the noise that the code is tailored toward, it performs well, but it falls off significantly in the other directions. Now, a maximum likelihood decoder is good to gauge the code capacity of codes, but it's not very efficient. And so we then decoded using an efficient matching algorithm. And the way we do this in the XZX surface code is, if you take a look at the way that Z errors propagate these -1 measurement outcomes or effects, they do so along these 1D diagonals, which we call as Z symmetries. And so in a noise model where there are only Z errors, there's always going to be an even number of defects along these diagonals. And so we turn what is usually a 2D matching problem across the whole surface of the code into multiple 1D repetition code matchings, of which the threshold is 50%. Now, when we also allow for some lower rate X and Y errors, these symmetries are now violated, but the way we correct now is we favor matching along the Z symmetry diagonals, and we penalize matching along the opposite diagonals, where the weights that we give there depend on the bias of the noise. And these are the thresholds that we obtain. So 50% at a bias of infinity for the XZX surface code. And even here, you can see that for biases greater than around 10, we're still matching this hashing bound. And the thresholds are also significantly higher than the previously best thresholds, which are those for the tailored CSS surface code. Because we're using a matching decoder, we can easily extend these to fault tolerant simulations, where we now allow the stabilizer measurements to be faulty. And we just perform the standard simulations where we stack up the syndrome at each measurement time and create a 3D syndrome volume where we can perform minimum weight perfect matching in. Now, time-like errors are these correspond to measurement errors. So we can see here that the thresholds are quite high. For biases smaller than 10, they exceed like 5%. And I'm running out of time, but I just want to say quickly that we also observe increased sub-threshold scaling compared to the standard surface code by a factor of the bias. So this is a summary of what I said. And yeah, so the main drawback of any surface code is that they have a vanishing rate. And an open question would be to see if we can do this symmetry matchings in other codes. Thank you for listening.
Thank you, Pablo, for the very nice talk. Does the audience have any questions? You can type your questions in the chat. If there are no questions, I have a question. So have you considered some other types of possible noise models to study in the future?
So this was probably the simplest noise model that we could come up with, which was biased, and drove the point across that we can indeed exploit the bias in the noise. But there has been work done already for even more complicated noise models, actually at the circuit level, circuit noise simulations, with those Karakat qubits that I was talking about before. And they demonstrate that we can still exploit the bias even at the circuit level.
Thank you, Pablo. So we are on to, so now is the time for the next talk. Thank you, Pablo, very much for your very interesting talk. Can we have the next speaker share the screen, please?
Yeah, I think Pablo just needs to stop sharing.
Oh, Yeah, there's a question in the Q&A, but now it's the time for, yeah. Yeah, so now it's time for, yeah. So now we're very pleased to have Paul tell us about universal fault-tolerant quantum computing with stabilizer codes. And just as a reminder to the audience, if you have any questions anytime during the talk, can you may just type directly in the chat, and I will ask the questions at the end. Paul, please, can you share your work?
Yeah, great, thank you. Can everyone see my screen? Is that okay?
Yes.
Yeah, okay, that's great, thanks. Yeah, so I'd like to talk about our work on universal fault-tolerant quantum computing of stabilizer codes. This is joint work with Michael Vasmer, Thomas Scrooby, and Stephen Bartlett. It can be found in this archive reference and, of course, in the pre-recorded talk on YouTube for the conference. So what I'd like to do just in 5 minutes is just go through a summary of our results in the big picture, and then I'll be happy to take questions. So our results really fit into two parts. First, we have a no-go result, which we argue is a much more general no-go result precluding a universal set of fault-tolerant gates than the number of earlier no-go results. And secondly, we show a way to circumvent our no-go result, which gives rise naturally to a framework for building universal fault-tolerant gate sets. So in particular, our starting point is to consider fault-tolerant gates. And it's important, I guess, fault-tolerant gates are important to building scalable quantum computers that are robust against noise. So building a universal fault-tolerant gate set is really what we need to do if we want to be able to have scalable universal quantum computing. And by contrast to previous work, such as that by Easton and Nill that considers very specific classes of fault-tolerant gates, we take a very general notion of fault-tolerant operations as those that preserve the protection provided by an error-correcting code. So in particular, we say that an operation or a gate is fault-tolerant if it preserves an error-correcting threshold throughout the process. And what we do is observe that standard threshold theorems are generally proven for a particular kind of noise or class of noise called local stochastic noise. So for that reason, it naturally emerges from this consideration that fault-tolerant gates can actually be considered those that preserve the locality of local stochastic noise. That is, they map local stochastic noise to local stochastic noise. And what we show then is that these local noise preserving operations naturally, necessarily are bounded in the extent to which they can spread errors. That is, the weight of an error under the action of such an operation can only grow by at most some constant factor. And we show that in turn, this implies that gates of this type that have bounded spread of errors are not sufficient to realize a universal set of gates on a range of standard codes. So taken together then, this forms a highly general no-go result, where we take a general notion of fault tolerance as local noise preserving operations and show that they're not sufficient for universal quantum computing on a range of stabilizer codes. And in particular, these, what I've called here standard codes, we show include most of the approaches that people are currently proposing for fault tolerant or error correcting quantum architectures. So it includes, for example, conventional topological stabilizer codes, including all two-dimensional topological stabilizer codes, as well as higher dimensional examples such as higher dimensional surface or toric or color codes. It also includes concatenated stabilizer codes. So between that, it covers a wide range of the most widely proposed stabilizer codes to be used for error correction. And we leave open the very real possibility that it may also apply to a much larger class, as we discussed in the paper. So the value of this general no-go result built out of such a general notion of fault tolerance is it really lets us understand how it can be circumvented in a really general way. So in particular, what we argue is that a natural way to go one step beyond these local noise preserving channels is to consider essentially local noise preserving channels, which are operations which only have this local noise preserving property on correctable errors, but are unconstrained in their action on uncorrectable errors. And what we show is that unitary operations of this type are a trivial extension of local noise preserving channels and are still constrained by our no-go result. But if we incorporate error correction into the implementation of a logical operator, this gives us non-unitary operations, which can have the property that they have a bounded spread of correctable errors. That is, correctable errors can only grow by at most some constant factor in weight, but can have an unbounded spread of uncorrectable errors such as logical operators. And we show that this first condition is sufficient for fault tolerance, while the second condition allows us to circumvent our no-go result. So in particular, the problem of building a universal gate set then breaks down to this idea of how we can incorporate error correction into an implementation. And we show that there are two natural ways we can do this. One is by using error correction by teleportation, which gives rise to procedures such as state injection and code switching. And the other is to intersperse error correction through the implementation of a logical operator, which gives rise to approaches such as code defamation and peaceable fault tolerance. And we show in the paper that taken together, these approaches and this general framework cover nearly all of the proposed methods for realizing universal set of gates fault tolerantly. So taken together then, what we have is a really general way to circumvent our no-go result, which gives rise to a general framework that can be used to build universal fault-tolerant architectures for quantum computing. And we believe that as well as being theoretically interesting, this could also inspire new architectures in contexts such as LDPC codes, where a lot is still unknown about how to realize methods of this type. So I'm happy to take any questions now. That's all I wanted to say about that. Sorry, I might have to just, sorry, I've stopped sharing. Are there any questions?
Thank you, Paul, for, do we have any questions in the chat? We have plenty of time for questions now. Thank you, Paul, for the very succinct talk. I'll just wait around a bit for the audience.
Yep.
Oh, so there's a question. From Seth. For a non-QECC or fault-tolerant person, how should I view this result?
Yeah, that's a really good question, because maybe I pitched this at quite a technical level. The big takeaway from this is that if we want to build a universal quantum computer that works even when we have noise, what we need to do is be able to know how we can do operations on information protected and error correcting codes that still work even when there's noise. So these fault tolerant operations are basically operations that still do what you want, even when there's noise afflicting our system, as there always will be in the real world. So it was known that there were lots of restrictions on what fault tolerant gate sets can do, and really a sort of trade-off between fault tolerance in terms of working in the presence of noise and trying to realize a powerful enough quantum computer to do all the quantum computations that we want. So what we've really shown is a more general version of lots of these no-go results, but also an understanding of how we can get around the no-go result to realize what we really need, which is this universal fault-tolerant gate set. So if you like, what we've really shown is that non-unitarity, I guess, was known intuitively to be an important thing that lets us get around no-go results such as Easton nil. In a way, what we've done is made that concrete and really shown how specifically incorporating error correction into the implementation of operation itself is what's really essential. And that sort of explains why it's possible to still realize these universal fault-tolerant gates even with the no-go results.
Thank you. There are two more questions. So I'll just go to the first one really. So there's a question by Dave Tuckett. How general is standard codes? Is finding non-standard codes a realistic way to circumvent the no-go result?
Yeah. So should I take that one first?
And there's another question. Are there specific ideas for universality that are inspired by this from Dominic Berry?
Okay, they're both really good questions. Yeah, so to take Dave's question, so absolutely. So one way around this would be to look for these, what we've called non-standard codes. So one promising type of candidate are more general LDPC codes, these low density parity check codes that still have the property that they have low weight stabilizers, but are a kind of generalization of topological stabilizer codes where the stabilizers aren't geometrically local. And we don't know whether they're constrained by a no-go result or not. So we find this property called infinite disjointness that we prove is a constraint on topological stabilizer codes and concatenated stabilizer codes. But it's an open question whether there are LDPC codes that get around that. So seeing if we can find an LDPC code with low disjointness would be a really good way to do that. So quickly take Dominic's question, are there specific ideas for universality that are inspired by this? So I guess the situation at the moment is what we found is really, in a sense, most of the natural ways that you could do it were already proposed when we were filling it in. I guess the one thing that we found that wasn't completely expressed in the literature was this idea of using code defamation. So code deformation is often looked at in terms of breeding defects in topological codes, and that's known not to be sufficient for universality. What we show is actually an example of how you can code deform between codes of different dimensions in a way that gives a universal gate set, a bit like code switching does, which is this other method, but it does it in a different kind of way. So that's something we talk about in the paper and in the longer talk. And it's interesting in this case that we show that it's possible to do this non-unitarily by allowing dissipation of energy with self-correcting codes without classical processing. So that's maybe one new type of approach that comes out of this.
Thank you, Paul. We are on to the time for the next speaker. So could you unshare your screen? And the next speaker could share the screen. Yes, so we are very pleased to have the next speaker, Senrui Chen, to tell us about recent advances in classical shadow estimation. Please tell us.
Yeah, thanks. So can you see the screen? Good. Okay, thanks. So hello, everyone. It's a great pleasure of me to present at TQC. So the title of my today's talk is Recent Advances in Classical Shadow Estimation, which is a merged talk of the following two papers. The first is Efficient Estimation of Polyobservables by De-randomization, which is a work by Xinyuan Huang, Richard Kun, and George Skill. And the second paper is Robust Shadow Estimation by Senrui Chen, which is me, and Wenjun Yu, Pei Zeng, and Steve Lamia. I want to give special thanks to Xinyuan Huang for help preparing these slides, and he will be there with us for the Q&A section. So let's get started. The motivation for this series of work is how to construct a classical representation of a many-body quantum system efficiently in order to accurately predict properties. Why do we care about the classical representations of a quantum system and to predict properties? Well, the first thing is definitely we want to know about the quantum system of our interest. And moreover, there are many hybrid classical quantum algorithms that rely on estimating properties of a quantum system. For example, the quantum variational eigensolver may require you to estimate the energy of an unknown quantum state. The classical shadow formalism, which is originally proposed in this paper by Huang Kun and Skill, is a method to deal with this property estimation problem. It goes as follows. Given an unknown quantum system of your interest, you first apply a random unitary evolution, and then you do a computational basis measurements. Repeat this for a few rounds. Then, based on the classical data you collected, you can compute a classical representation of the original state of interest. And this classical representation is referred to as a classical shadow of the original quantum system. And based on this classical shadow, you can predict any properties of your interest about the quantum system. The good thing of using a classical shadow formalism is that it has a very good theoretical guarantee on the sample efficiency, as stated in this theorem. So there exists a procedure that guarantees the following. Given parameter b epsilon, the procedure can learn a classical representation of an unknown quantum state rho from b times log m over epsilon square measurements, so that subsequently, given any set of m observables, such that all of these observables has a shadow norm upper bounded by b, then the procedure can use the classical representation to predict the expectation value, trace OI times rho to an additive error epsilon for all these index I. So as an example, if we're given 10 to the 6 observables, then naively we would expect 10 to the 6 over epsilon square measurements in order to predict all the expectation value. But thanks to the classic shadow formalism, we can use only like a 6 times log 10 over epsilon square measurements to complete the expectation estimation of the expectation value, which is a great saving in the sample complexity. We need to mention that the sample complexity of the classic shadow formalism depends largely depends on the quantity that is known as a shadow norm of the observable of interest. And this shadow norm can be calculated once you decided what kind of unitary evolution you want to do in your system. As a special cases, if you're interested in estimating poly observables, then classical shadow formalism actually shows that to estimate any m few body poly observables, an order of log m copies of rho will suffices using only single copy local measurements, more specifically just using poly measurements. And in these cases, the shadow norm can be calculated with this formula. Okay, so a question stems from this previous work is that, is there a way to estimate arbitrary polyobservables? Can we still achieve a similar scaling of log m? This question is at least partly answered in another work by Huang and Preskill, which shows that for any m arbitrary polyobservables, probably a high weight polyobservables, an order log m copies of rho still suffice to predict the expectation value for all of them. But the problem is that the protocol will require an entangled measurement on all the copies, which means that you have to take multiple copies of rho together and apply the large joint measurement on that, which is obviously very difficult to implement on near-term quantum devices. So the problem now left to us is that, okay, can we improve the algorithm? Can we have an algorithm that only using single copy local measurements, but that can still efficiently predict a set of arbitrarily high weight polyobservables? And this is the main concern of this paper, efficient estimation of polyobservables by de-randomization, which is one of the main topic of today's merge talk. In this paper, the author actually proposed a way to learn a measurement procedure for a given collection of polyobservables by de-randomizing the randomized measurements. So the idea here is that, okay, instead of doing a randomized choice of poly measurement, they can actually using some cost functions to calculate a best knowledgeable choice of deterministic poly measurement scheduling, such that it will give you more information about the polyobservables of interest compared to a random measurement. So you can see more detail in their paper or in the pre-recorded talk. And the key theoretical guarantee here is that the de-randomization will always perform at least as good as the original randomized measurement protocol. And in certain applications, the de-randomization algorithm actually has a much better performance. Here is two applications from about this polyobservable estimation method. The first is in estimating ground state energy in molecules. We can see that the de-randomization shadow as represented in this blue line, and the original randomized classic shadow as represented in this line. For the similar number of experiments, the de-randomized method will have a much smaller estimation error compared to the original randomized one. Yeah, and in another numerics about finding eigenstate in 1D electrodynamics model, we'll see a similar effect that the de-randomized shadow would need a much less number of experiments compared to the randomized version in order to achieve a similar level of precision. Yeah, great. So now it's time to come to different topics about classic shadow. That is the noise for classic shadow. The original classic shadow formalism actually assumes a perfect implementation of the random unitary and the measurements, but in a realistic experiment, both items would actually suffer from experimental noise. So a question for us to ask is, can we make classic shadow noise resilient while still retains its sample efficiency and simplicity for implementation? This question is answered, at least under some noise assumption, in our paper, Robust Shadow Estimation. So the idea of robust shadow estimation is a protocol in two stages. The first is the calibration stage, where we prepare a probe state that is known and fixed, and we apply a random unitary evolution and computational basis measurement on that, repeated for a few rounds, and use the data collected. We can do a noise characterization procedure. After the noise characterization, we can go to the estimation stage, where we prepare the unknown quantum state of our interest and doing a similar unitary random evolution and apply measurement and using the data to do property prediction. So the idea here is that thanks to the calibration stage, we can use the information from the noise characterization to debias the effect of noise in the circuit in the property predictions of our estimation stage. And actually, thanks to the random circuit in the classical shadow formalism, we can show that the noise characterization can actually be highly sample efficient. So here is one of our theoretical guarantee. Given the following two assumptions, the first is that the noise in the circuit is gate independent, time stationary, and Markovian. The second is that the computational basis state cat0 tensor power n can be prepared with high fidelity because we want to use this state as a probe state. Then there will exist a procedure that use local random measurements and that can debias the classical shadow estimator of any k-body observables to an epsilon bias using c to the k times epsilon to the minus 2 times fz to the minus 2 measurements, where the fz here is something called a z-basis average fidelity of the noise channel, and c here is only a small constant. So the key idea here is that the whole procedure is sample efficient for few body observables and not too intense noise model. And interested reader can see our paper for full analysis about other group of unitaries, about total sample complexity and relaxation of both assumptions. Here we present two numerical experiments of our paper. The first is estimating correlation functions in a 1D Ising model ground state under bit flip error. The second is estimating ground state energy of a H2 molecule under imprecise pulse control. In both cases, we use a similar number of samples for both the standard classical shadow method and our robust shadow estimation method. And we can see that in the blue line, our robust shadow estimation method can give a much more accurate prediction of the property of the quantum state. Yeah, good. So now it's time to conclude. So classical shadow is a rigorous and practically efficient randomized procedure that allows your classical machine to predict properties of a quantum system. And in today's talk, we introduced two recent advances in this direction. The first is that de-randomizing the procedure can actually provide a significant speed up in many applications. And second is that the robust shadow estimation procedure provides us an efficient way to mitigate experimental noise in property estimation, at least under some reasonable noise assumption. So with this, I would like to wrap up, and Xinyuan and I will be happy to take any questions. Thank you.
Thank you, Senri, for the very nice talk. Are there any questions from the audience? You can type them in the chat or the Q&A. I'll just wait. We have 2 minutes for questions. Okay, so I have a question. So what are some, I'm not very familiar with this shadow estimation. So I was wondering like what applications this type of procedure has.
Yeah, Xinyuan, do you want to answer this question?
Yeah, sure. I guess if you go back a few slides to this application slide that we had. So like, for example, you could allow more efficient estimation of ground state energy in molecules in like, let's say, quantum chemistry applications. If you only focus on applying, like for example, this one, it would be focusing on applying single qubit rotation plus computational basis measurement. I think previously what people would do is they would try to find like qubit-wise commuting observables to group them, which is this red line, this LDF grouping based on largest degree first grouping strategy in order to simultaneously estimate different Pauli observables. However, by applying this de-randomization approach to the original classical shadow estimation, we found that you can actually much more efficiently estimate the ground state energy in small molecules, such as like the ones that's considered on the right-hand side. We also consider it for like estimating this Hamiltonian variance, which is a sum of 4 body terms in a lattice Stringer model. And we also found that like applying this de-randomization approach for classical shadow also substantially improves the number of experiments that you required in order to estimate this Hamiltonian variance, which is needed to find eigenstates for this quantum field theory model. So these are two applications of it, and there's actually more. Like, for example, you could estimate entanglement ready entropy of your system. Also, you could utilize this classical shadow framework to estimate topological entanglement entropy, which is actually being applied in one of Google's recent paper about implementation of service code using their device, and they wanted to like verify that they actually constructed the toric code by measuring topological entanglement entropy. So these are just some applications of this kind of framework. So.
Okay, thank you, Senri and Xingyuan, for sharing with us your work on shadow estimation. Now, could you, Senri, can you stop sharing the slides so we can have the next speaker, Kun Wang, to share the slides? So we're very pleased to have Kun Wang share with us his work on measurement error mitigation via truncated Neumann series.
Okay, hello everyone, can you hear me?
Yes.
Okay, I'm Kun Wang from Baidu Research. So first of all, I want to thank the organizers and the chair for hosting this TQC conference. In this talk, I will briefly introduce our recent work on measurement error mitigation via truncated Neumann series. It introduces another kind of error mitigation technique to deal with the measurement noise in near-term quantum devices. You can see the previous talk by Chen also introduced a way to mitigate the measurement and gate noise. So what is measurement noise? On near-term quantum processors, the measurements are subject to hardware imperfections. So this will need to read the so-called read-out noise. So ideally, we will prepare the initial state and perform some unitary evolution. In the end, we perform a measurement, and we want to get an ideal probability distribution. However, the bit truth is that the measurement would suffer from some, say, calibration noise or noise from the environment. So we can only obtain some noisy probability distribution. To start, this is the current situation. So to study the noise, we have to first set up the model. Luckily, we can see that the measurement noise can be understood purely as a classical noise. What does this mean? It means that the noisy measurement can be understood as an ideal measurement followed by a classical perturbation. So you can think like here, we have a noisy measurement. Inside it, we first obtain the ideal probability distribution. However, some bad guy said if he randomly permutes the ideal probability distribution, so we can only obtain a noisy one. The classical perturbation can be modeled by a clone stochastic matrix A of size 2 to the n power n. What's more, A can be learned by calibration procedure. So the problem is that we assess the calibration noise matrix A and the noisy probability distribution P noisy. How can we get the ideal probability distribution? This is the question. We consider a concrete task. In this task, we want to compute the expectation value. So in this task, someone will generate a target state row. It may be generated by some ideal quantum circuit, and we measure the state, but the measurement is noisy. And then we use a noisy probability distribution to compute the expectation, the task trace O row. We want to obtain the this value. This task is very common in near-term algorithms, say the VQA algorithms. Ideally, we can compute the expectation trace overall via, we can enumerate all the bases and multiply the observable with the probability distribution. However, in the practical case, if we adopt this kind of computation, then A comes to play, the ideal probability distribution is disturbed by A. So we can only obtain some noisy expectation value. Our problem is to correct the effect of A and obtain the ideal value. So intuitively, if we can compute the inverse of A, then we can recover the ideal value easily. However, compute the inverse is very difficult and expensive. Now let's see another way to solve this problem. Before going to the details, we introduce a mathematical tool called the Newman series. This theorem says that for a square matrix A satisfying certain constraint, then we can decompose its inverse as the linear combination of different orders. So you can see the expressions in red here. A can be approached by a linear combination of different orders of AK and with some remaining term. Use this tool, what we can obtain. If we apply the Newman series to mitigate error, then we can see that we insert the A inverse here, and we reorganize the terms. We would obtain that the ideal value would be a linear combination of some noisy expectation values of different orders with a bounding term. So we have two tasks. One is how we can compute the expectation values of different orders. Another is how we can bound the remaining terms. For the first task, we can go to the details. So if we look in deep at the expectation value of order K, we can see that it's actually obtained by a noisy measurement whose noise matrix is A to the power K. So how can we obtain the effective noise matrix A to the power K? It can be effectively simulated by K sequential uses of the noisy measurement device. So if we use the measurement device once, we obtain A. But if we use it twice sequentially, we would effectively obtain A to the square. And this goes on and on. That means we can use the measurement devices several times to obtain different values of order K. Okay, this is how we obtain this value. The second is that we have to bound the estimation error. So then luckily we can do this because we can show that if we consider only the first K terms, truncated terms, then we can find its value to the ideal value is upper bounded by exponential decay. Where chi is the so-called the noise resistance. It is directly related to the original noisy matrix, the minimal diagonal element of the original matrix A. So from this theorem, we can see that the approximation error is exponentially decay based to the number of truncated terms here, and the noise resistance is directly related to the minimal diagonal element. That is to say, we only need to know the a specific parameter of the original noise matrix A. Then we can determine how many truncated terms we need, and then we can approximate the original ideal value pretty good. Okay, this is the core contribution of our talk. And for more details, especially the experimental results, simulations, I would refer you to the archive version here. Thank you.
Thank you, Kun Wang, for your very nice talk. Are there any questions from the audience? You can ask them in the chat or the Q&A. Oh, also there's a question so how do you learn A efficiently?
A cannot be learned efficiently. We assume A is already obtained by some calibration procedure. However, to compute the inverse of A is very difficult because, as we know, the most efficient method to inverse a matrix is exponential. Has a complexity of exponential difficulty.
We still have time for maybe one more question. Just wait a bit. Okay, if there are no more questions, I'd like to thank all the speakers for this session. And so the next session will begin in about half an hour.
Hello, hello, hello. Only one.
Hello. welcome to the last session of the morning today. Can the next speaker please share the screen?
So can you see my screen?
Yes, we can see perfectly. Can you make it a full screen, please?
Sure.
Welcome to this session of TQC. We're very pleased to have Yoshifumi Nakata to tell us about explicit constructions of exact unitary designs and applications to randomized benchmarking.
Okay, thank you for the introduction. So let's start my talk. This talk is about unitary designs, and I'm going to present two results. One is about the new construction of exact unitary designs by quantum circuits, and the other is an application for of the unitary designs for benchmarking noisy quantum devices. So our paper is already available on the archive. So if you are interested, please visit our paper. Okay, so let me start step by step. So what is a unitary design? Unitary design is defined by a finite set of unitaries that mimics a Haar random unitary up to the tth order statistical moment. So here we have technical terminology, Haar random unitary. I think we have already heard this word many times. But a Haar random unitary is just a uniform distribution of unitary matrices. So let's say we have a unitary group acting on n qubits, and then we just consider uniform distribution. And if we randomly pick up one unitary from this uniform distribution, that is called a Haar random unitary. And when we talk about unitary designs, we want to mimic some properties of a Haar random unitary by finite ensemble of unitaries. So here is a kind of diagram of a unitary T design. And T is a parameter that indicates how uniform the distribution is. And T is a positive integer. We have 1 design, 2 design, 3 design, etc. And if T goes higher, then this distribution approaches a Haar random unitary. So this is a basic idea of unitary designs. And why do we care about this? The reason is there are many applications of unitary designs in quantum information processing. For example, we can use designs for quantum communication, computation, and also cryptography. So there are so many protocols that use unitary T design. But for general T, we don't know how to exactly construct the unitary T designs by quantum circuit. And indeed, we know only approximate constructions of T designs that works for general T. And for example, exact construction of unitary T designs has been a long open problem in combinatorial mathematics for more than 40 years. So it's highly non-trivial to construct unitary T designs exactly. So this is the background of our work. And in this talk, we provide a quantum circuit for exact unitary T designs for any T on arbitrary number of qubits. So this is our first main result. And the second result is we use the first result to generalize the randomized benchmarking protocol. So let me first explain the first result. So our strategy to construct exact unitary T designs is to use inductive quantum circuits in terms of the number of qubits. So we first generate exact unitary T design on a single qubit. And we just use inductive quantum circuit to extend this single qubit T design to any number of qubits. And this is a kind of inductive quantum circuit. So we just assume that we have a T design on n qubits. And we just make all the unitaries in the T design controlization. So this is a controlled unitaries. And after that, we apply single qubit rotation controlled by n qubits. And we just repeat this multiple times. And we can actually show that this quantum circuit forms an exact unitary T design on n plus 1 qubit. So we can generate T design on n plus 1 qubits from those on n qubits. So this is our first main result. And the point in this circuit is we have to choose these angles very carefully. And these angles can be determined by solving the so-called zonal spherical functions. They are just symmetric polynomials. So we can just, in principle, solve it in advance. So we know these angles, and we can construct this inductive quantum circuit. So this circuit is a first explicit construction on exact unitary T designs. That means we have solved the open problems in combinatorial mathematics. And I believe that this is a kind of good theoretical progress in the theory of designs. But unfortunately, this circuit is inefficient because we are using inductive constructions. So if we expand all of these T designs, the number of T and the number of 2-qubit gates explodes exponentially. So this circuit is actually inefficient in terms of the number of qubits. So this construction is of practical use only in small systems. So this is a brief overview of our first result. And then let's move on to the second main result. It's about the generalization of randomized benchmarking protocol. I think many people are familiar with randomized benchmarking. For example, we can use standard RB, this is a randomized benchmarking, to estimate average gate fidelity based on a unitary 2 design. So basically, we use Clifford's group, but Clifford's group is an exact unitary 2 design. So this is a protocol of standard RB. So we essentially just apply noisy quantum gates many times, and we choose these gates from a Clifford group or an exact unitary 2 design. And by doing this, we can estimate the average gate fidelity of these gates. So this is a standard protocol of randomized benchmarking. And our idea is to use unitary 4 designs instead of 2 designs. And we just basically do the same protocol as the standard RB. And we call the new protocol second order RB. So this is just a generalization of standard RB. And we can show that from this second order RB, we can estimate unitarity and self-adjointness of the noise acting on the gate. So what is unitarity? Unitarity is a metric of noise, which is related to quantum error correction. So in the literature, people investigated the relation between unitarity and quantum error correction. So if we know the unitarity of the noise, it's good towards the realization of quantum error correction. On the other hand, the self-adjointness is a new metric that we have proposed in this work. And we also argue that this is relevant to a practical feasibility of quantum error correction. So this is a new metric, but it's also related to quantum error correction. And both of them can be estimated by using the second order RB. We also did some experiments of the second order RB in a superconducting qubit. But if you are interested, please visit our paper. Okay, so this is summary and future problems. So in this talk, we have provided a quantum circuit for exact unitary T designs for any T on arbitrary number of qubits. So this is the first construction, explicit construction of exact designs. And we also presented some generalization of randomized benchmarking. So there are many future problems. So if you are interested, I'm happy to discuss. So thank you for listening.
Thank you, Yoshifumi, for the very nice talk. Are there any questions? You can type them in the Q&A or the chat. I saw a raised hand just now. I'll wait a bit. Are there any questions? Well, if you're still thinking about your questions and the next talk begins, you can still type your questions in the chat, and the panelists will be able to answer your questions. So I think it was a very interesting talk. So if there are no questions, I'd like to thank Yoshifumi for this very excellent talk. And so could you unshare your screen?
Yeah, thank you very much.
And the next speaker can please share your screen.
Sure.
Okay. Please share your screen.
Yes, can you see it?
Yes, it's perfect. Today we're very pleased to have Daniel Stupranka to talk to us today about fast and robust quantum state tomography from few basis measurements.
Okay, thanks a lot for the introduction and for the opportunity to speak here today. So this is joint work with Fernando Brandão and Richard King, and it's available on the archive. And as you and this is a talk about tomography of quantum states of low rank. So the problem we want to solve is as follows. You're given access to some copies of a state rho in dimension D, and you're promised that it is approximately of low rank R. You're only allowed to measure individual copies of rho, so you're not allowed to hoard them in a quantum memory and then measure them collectively at once. So it's a single copy measurements. And the goal is to obtain a classical description of a state rho prime that is close in trace distance rho. So that's the problem we want to solve. And of course, there has been a lot of work on this in the literature, and there are many relevant resources to optimize for. So for instance, the number of copies of the state, we need the number of measurement settings, that is how many different bases we need to measure, how expensive the classical post-processing is, what is the classical memory we need, which turns out to be a bottleneck in many proposals. And there are also some other more qualitative aspects an algorithm should have. For instance, it's being robust to both statistical noise and also noise in the measurements. It's also desirable that it has an online implementation. That is, you can already start the reconstruction as you're gathering the data. And furthermore, you want your measurements to be as simple as possible so that the experimentalists can actually implement them in the lab. And we either match or improve all other results in the literature, in all the resources I mentioned before, if up to a worse dependency on the error. So for instance, for the memory required to do the post-processing, we essentially only need D times R. So it's also the number of parameters which you need to describe a rank R state up to this epsilon to the -2 dependency. We also obtain, and we also match many of the known lower bounds, again, up to a worse dependency on the error. Moreover, we're also able to get rigorous guarantees for other measurement setups that were out of reach for previous techniques. For instance, random Clifford measurements. I should also say that our algorithm is provably robust, both to statistical and also experimental noise. We get a quantum speedup for doing tomography. So if you, instead of doing it on a classical computer, you do it on a quantum computer, the runtime is actually d to the 1.5. And here I'm always suppressing the polylog terms, and everything just holds up to a constant probability of failure. Okay, so what's the intuition as to why we obtain a better algorithm? First, for the sample complexity and measurement settings, our setup gives a easy way of converting the bounds on how distinguishable two states are in the random measurements into sample complexity bounds for complexity. And then we can just use import other results from the literature on distinguishability of states in the random measurements to get our sample complexity and basis settings bounds. For the runtime, we use the fact that our algorithm is very robust, and then we can only work with rough approximations. And in particular, if we use the measurements, like if the measurements are described by local quantum circuits, then it is possible to actually reduce the whole procedure to just doing sparse matrix vector multiplication, which can be done in time d squared instead of d cubed, as we never have to actually diagonalize any matrix. We only have to do sparse matrix multiplication. So that's why we obtain a better runtime. And for the memory, the runtime stems from a similar comes from a similar reason, namely the fact that at each step we actually only need to store some very sparse matrices, so either local quantum circuits or diagonal matrices, and that's how we obtain a better memory as well. And I'm just going to illustrate quickly how the algorithm works with a 1-qubit example. So it works like this. We start by assuming that the state we're given is the maximally mixed state, which is here in the middle of this block sphere. We then choose a random basis and see how the statistics with respect to this basis compare with our current guess and the target state. And based on the information, and that is how the two histograms differ between the target state and our current guess, we actually update the state, and then we choose different measurement bases and continue updating our guess until it converges. And we know how to check if it converges by actually, again, measuring a couple of random bases and then noticing that they are undistinguishable under those bases. So that's more or less the intuition of how the algorithm works. And as I mentioned before, there's our algorithm is very good up to this bad dependency on the precision you want to obtain. However, in practice, we don't observe it. So it would certainly be nice to show why it is the case that we don't have this bad dependency on the precision in practice. And I would also say that it is very easy and fast to implement this algorithm. It really indeed requires less memory and less programming time than other approaches. So because of that, I think it could be used to perform tomography easily on larger system sizes. So again, I would claim that this algorithm is also practical in spite of this bad dependency on the error in the current theory we have. And with that, I would like to thank for your attention and be happy to take some questions.
Thank you for the very nice talk. If there are any questions, you can type them in the chat or in the Q&A. We have plenty of time for questions. So I'll just wait a bit.
Sure.
Okay, so maybe I have a question. So my question is this sounds to me a little bit like a quantum metrology type of problem, because you're doing this estimation. So do you think there would be is there any way to compare these protocols here with an approach that would be taken using quantum metrology?
I'm not so sure, but I think that in principle maybe you could use some metrology approaches to get better ways of indeed distinguishing the two states, because I mean at every step of this algorithm you have to like either you have to distinguish your current guess from so your hypothesis from what you actually have. So I think that indeed like using ideas from metrology, or maybe using the fact that usually you have at least some vague intuition of what your state should look like, that incorporating this into the algorithm should give you better convergence guarantees. But here we're working in this very general setting where you don't know nothing about your state. But I think the algorithm allows for easily incorporating like extra knowledge or other techniques to distinguishing states into it. Yes.
Thank you for the very informative answer. So just so if there are no further questions, we'd like to thank Daniel for sharing us your work today. And so could you please unshare your screen? And
Sure.
The next speaker can now share the screen.
You see this?
Yes, I can see it perfectly. Yes. So we are very pleased today to have Han-Chien Lin to share with us his work on sample-efficient algorithms for learning quantum channels in the packed mode and the approximate state discrimination problem.
Thanks for the kind introduction, and thanks for everyone to come in and talk. I'm going to talk about this work as a generalization of the classical packet learning shadow to quantum channels. And this is a joint work with Fang. So let's start with the classical packet learning shadow. Excuse me, the classical packet learning model. So in the packet learning model, we are given a concept plus C, and it's just a set of Boolean functions. So every dot here is a Boolean function. And there is a target concept C star that we want to learn. And we learn C star by getting samples. That's just pairs of input-output pairs to this C star. And where the inputs are drawn from some unknown distribution D. And this is called probably approximately correct, because for probably, this learner only needs to learn with probability 1 minus delta, and approximately correct because the learner doesn't need to output this C star exactly. He only needs to output the hypothesis H, that is epsilon close to C star. Now this epsilon close is actually defined by this distance measure. That is a probability that the output of C star is different from the output of this hypothesis, and when the input is drawn from this unknown distribution D. And here we want to study the information theoretical problem of sample complexity. That is just the number of samples. Samples here you need to draw to learn to this epsilon and delta. And now we generalize this to quantum channels. So obviously we generalize the Boolean functions to quantum channels from some Hilbert space to another Hilbert space. So we still have this concept class, and we still have a target concept we want to learn. And now the learner gets these samples that are input and output pairs to our quantum channel. But now these are quantum channels, or the input output pairs are quantum states. Now there is something to decide for our model. For quantum state, there are two ways to give information about quantum state. You can either give a full classical description of your quantum state, or you are just given some copies of the unknown quantum state. Now, because of a non-cloning theorem, it's not very natural to have the input and output both as unknown quantum state. So just assume we have the full classical description of our input, and we are keep getting one copy of the output as a unknown quantum state, and that keeps the quantum nature of the problem. And now the learners still want to learn according to some epsilon and delta. And there is a natural generalization of distance from this probability of output being different to the expected trace distance between the output. And they want to study the sample complexity. Now this is kind of a summary of our work. So the comparison. The sample complexity of classical pattern is pretty well studied, and it can be written as this big theta of log size of the concept class plus log 1 over delta over epsilon. And in our work, we give two pretty good upper bound to the quantum packet learning. So the first one, you need the HR assumption that all the output states are pure states. In this case, our algorithm also have this log C dependence, log size of the concept class dependence. It's very similar to the classical result. And if the output state can be mixed, then we have this more complicated algorithm that has order log 4C dependence. And the highlight of these two algorithms is that this sample complexity is independent of the dimension of output state. Remember, we are giving the output state as an unknown quantum state, and it's quite unnatural to have some kind of learning thing to unknown quantum state that's a sample complexity independent of the dimension. And for the lower bound, we have a not quite matching lower bound of omega log C that is obtained by putting an epsilon and then a counting argument. And now I also want to talk about this approximate discrimination problem. It's actually a restrict problem of the quantum packet learning, where we restrict all the channels to have constant output. So in this case, every channel is just represented by this constant output, and our input doesn't matter. We're just trying to learn one quantum state from a whole bunch of quantum states. And call this approximate state discrimination because it is really similar to a well-known quantum state discrimination problem, where you are given a whole bunch of quantum states and you learn and want to copy from one of them, and you want to decide which one either is equality. This is the approximate version because it only needs to be S1 approximate. And this is actually a hybrid between quantum state topography and the quantum state discrimination. And for this approximate discrimination problem, we are also given algorithms. Actually, what we did is kind of reverse order. So we have all these two algorithms, sample complexity as our quantum learning algorithms. So we given these two algorithms first, and because the approximate state discrimination problem actually capture the hard part of quantum peg learning. So we just have those two algorithms and upgrade them to quantum peg learning algorithms. And as I said before, the highlight of this is that it doesn't depend on the dimension of the quantum state to be learned. So unlike tomography, this doesn't depend on Hilbert space dimension. And also unlike the state discrimination, it doesn't require a minimal distance between the states. So this is some table comparison between different quantum state learning problems. So here is our quantum state discrimination. You can see that it kind of takes both the easy part of quantum state discrimination and the quantum state tomography. So we take the assumption that our unknown states come from some state to the learning node, and also that the output state only needs to be epsilon close to the true state. And you can see that the sample complexity is kind of better than both of them. It doesn't depend on this D here, and it doesn't have this F requirement. F is the maximum fidelity between different states in S. And once again, this is a summary of our result. So when the output state are pure, we have algorithm with log C dependence, and output is mixed. We have algorithm with log 4C dependence. So thank you.
Thank you, Han-Chun, for the very nice talk. Are there any questions from the audience? We have about 3 minutes for questions, so plenty of time. Okay, I have a question. Do you have any plans for future? Do you have any plans for future work in this direction?
Future work, actually, there are actually independent work kind of follow up that is, so this is about peg learning, and there are different models like agnostic learning, and there is actually independent work that do this kind of in the agnostic model and kind of a greater sample complexity. So that's something, and you can always think about what's maybe you can get a time efficient algorithm for this, and that's also a nice way to think about it. I also see one question here. So C,
yeah, we have a question. Yeah.
So the C is the size of the concept class.
Yeah, I'll just read for the benefit of those who did not see the question. What is the size of C in the sample complexity result?
Yeah, size of C is the size of this concept class, so just the number of concepts in this big circle.
Are there any more questions? Well, if there are no further questions, we'd like to thank Han-Chun again for the excellent talk. And so, Han-Chun, could you share?
How do I?
You have to click on the green button.
Okay.
And then the next speaker can share the screen. Jonas Helsen. Hi.
All right.
Oh, yes. So we're very pleased today to have Jonas Hausen to tell us about the general framework for randomized benchmarking.
All right, perfect. Hello, everyone. So this is, as mentioned, a general framework for randomized benchmarking, which is a paper I wrote at the end of last year that you can find here together with Ingo, Emilio, Albert, and Jens. It's a fairly big group, and it's also a fairly large paper, and I'm only going to cover a small part of it now, and I'm going to cover a slightly larger part of it in the rest of the larger talk. So what is this about? So a framework of randomized benchmarking is about randomized benchmarking, of course. And so what is randomized benchmarking? Randomized benchmarking is maybe like it's sort of the standard method for estimating average fidelities of quantum gates. So if you have a quantum computer and you want to estimate how good your gates are, one of the things that you could do and that people end up doing quite often is something called randomized benchmarking. And the way it works is you actually estimate the quality of a gate set. So you have some set that is often a group, this G over here, and you can imagine this being the Clifford group, but it can be something else. And then the way you estimate the quality of this set is you start from some initial state, and then you apply in sequence M randomly selected elements from that group, and you sort of apply them to your state. And then you compute classically what the inverse of that whole sequence should be. So the total thing is ideally the identity. You apply that inverse and then you measure. And this gives, if you then sort of average over a whole bunch of random sequences, this gives you a number P of M that only depends on, that ideally sort of only depends on M, and under sort of reasonably broad circumstances, hopefully this data would decay somehow exponentially. And then from the decay rate of this exponential, you can extract somehow the quality of your gate. So this exponential decay rate is, under certain assumptions, directly related to how well your gate works. And I've sort of given the general idea here. And the goal of our paper, so and this sort of general idea has been formalized in many different versions. As far as I can tell, there's like somewhere between 35 and 40 different versions of this protocol that all do slightly different things. And our goal in the paper and also in the main talk was to give sort of a unified framework for randomized benchmarking in which you could fit all of these protocols and then prove that under very reasonable conditions, this protocol behaves as it should, namely that it outputs data that is to a good approximation exponential decay. And also, as a sort of consequence of the way we formalize this framework, you also get some really neat post-processing schemes, sort of generic post-processing schemes based on the theory of group algebras that I'm also going to talk about a little bit today. So for the pitch today, I'm just going to talk about these two things here. And then in the main talk, I'm also going to talk about this unified framework. And these other two things are also very interesting, but you have to go find them in the paper. All right, so let's talk about this behaves properly. So what do I mean with behave properly? The sort of central dogma of randomized benchmarking is that representation structure defines data structure. And what do I mean by that is that you have your set of circuits, which ideally forms a group. And the set of circuits defines a certain representation omega of your group. And sort of the central claim of randomized benchmarking is that if you do randomized benchmarking with this group and somehow the implementation of your gates is sufficiently well behaved, it's close to this representation in a sense that I'll formalize more, that is more formalized in the paper, then this data, this P of M, looks like a linear combination of exponential decays where each entry of the exponential decays is precisely set by an irreducible sub-representation of this sort of defining representation. For instance, for the Clifford group, you have sort of two representations. So you get two exponential decays, one of which is sort of trivial, so you get one exponential decay. But if you plug in another group, you can get wildly different behavior. In particular, this is one of the things that we've sort of also worked out in the paper, like these lambdas don't even necessarily have to be scalars. They could also be matrices if these representations show up in multiplicities. And then a big chunk of the work that we do is try to justify this sort of semi-folkloristic claim, which of course was rigorous in many cases already, try to justify it in full generality. So for arbitrary groups, arbitrary representations, and under the widest notion that we could think of gate implementation and close. And the way we do that is by taking a page from a really interesting paper by Pritchett, Merkel, and Fong from 2018, where randomized benchmarking is linked to the Fourier analysis of group functions. And this is sort of really the key trick that comes in, and they did it for the Clifford group, but it sort of works in general. And this means that you can take your randomized benchmarking data and sort of map it to the power of some matrix, a power iteration of a matrix, where this matrix is sort of the Fourier transform of your gate implementation. And then you can justify this formula by doing a fairly sophisticated bit of non-normal perturbation theory in this Fourier space, and like taking this matrix and perturbing it a little bit, which corresponds to sort of the noise in your gate implementations. But as long as this perturbation is sufficiently small and they're fairly broad conditions, this formula actually holds up to an exponentially small correction. So we can sort of prove in absolute generality that this works. And the tricky part here is finding what the good norm is, like what a good measure of distances on gate implementation functions. And it turns out that it's essentially the average diamond norm, which is slightly surprising. You could ask questions about that. And I'll go into a little bit more detail about this in the talk and also in the paper. So that's sort of big claim number one, which is that randomized benchmarking data essentially behaves in this sort of linear combination of exponentials way that is completely governed by the representation theoretic structure of your implementation set of circuits. And then once you have this, you can start doing all kinds of cool things with it. And so one of the things that we also generalize is this idea of post-processing schemes. So a general problem that people have been having with randomized benchmarking procedures when the gate set is not the Clifford group is precisely that your data is not a single exponential, it's a linear combination of exponentials. And this is, of course, perfectly expected. But these multi-exponentials are extremely hard to fit in general. So for more than a few exponential decays, you get into trouble. So the question becomes immediately, can we isolate like a single exponential decay by post-processing our data classically? And it turns out that the general trick, and this has sort of been rediscovered in special cases a few times, and we now sort of do the general case, is that if you don't invert to the identity in randomized benchmarking, but instead you invert to some global ending gate G-end, then you can essentially think of your probability data, your end data averaged over your sequences as a function from your group to the real line, which means it's an element of the group algebra. And then you can say, aha, I have this element of the group algebra now, and it's sort of a linear combination of these representation associated functions. Let me check my time. Can we now isolate it? Yes, because irreducible representations are precisely an orthogonal basis for group functions. And this leads you to a really nice sort of general protocol where you take inner products with elements of these orthogonal bases with this probability data to precisely isolate, oh, sorry, this should be a lambda instead of an m, to precisely isolate one of these single exponential decays. And of course, this doesn't work in general. It's not so clear that this works in general because this number here is not necessarily small with respect to the number of qubits, but we can prove sort of rigorously that it always works if your P of M that you measure in is a 3 design, which has some interesting connections to these newfangled shadow tomography schemes that we're sort of interested in figuring out in the future. All right, that was it. Thanks for listening to me, and be sure to check out the slightly larger talk and also the paper. Thanks a lot.
Thank you, Jonas, for this very nice talk. Are there any questions from the audience? Well, if you have any questions, you can always type them in. Oh, I guess Jonas is also giving the next talk. So maybe while the audience thinks about their question for this talk, they can listen to the next talk. Jonas, please.
Right.
Yeah,
let's just thunder ahead with the next talk, which is in some sense a specialization of this slide. So remember this technique when we go to the next few slides, because it's going to come in handy there. So welcome to my talk, which is called Match-Gate Benchmarking, Scalable Benchmarking of a Continuous Family of Many Qubit Gates, which is also a randomized benchmarking talk. And this is work I did also at the end of last year, together with Sefer Nazami, Matthew Riga from Rigetti, and Michael Walter. I would like to point out that there is sort of a really interesting related work that you should definitely check out and you can find on the archive here. Okay, so what am I talking about here? Well, obviously I'm talking about randomized benchmarking again, which, as I've said before, is this sort of averaged protocol that gives you average fidelities averaged over a gate set. And an interesting thing that I wasn't super explicit about before is that in all randomized benchmarking protocols so far, and also in the previous talk, we always assume that this gate set is discrete. And this is sort of important for a few reasons. But recently, people have gotten really interested in continuous gate sets, because continuous gates are things that are useful if you want to do VQE or QAOA. So naturally, we're now also interested in, can we benchmark these sort of continuously parameterized gate sets? And this is not, it turns out to be not so easy, but there is one really nice gate set where it is actually possible to do randomized benchmarking, provided you use this sort of more advanced methods of signal processing. The sort of naive randomized benchmarking is going to run into some trouble. All right, so what is going to happen? We are going to do randomized benchmarking with something called the match gates, and we're going to add some bit to it, which we call orthogonal match gates. So what are match gates? Match gates are a continuous set of unitaries. So it's an infinitely sized set, and it's also a group. It's closed under multiplication. And it's generated by, if you put all your qubits on a line, it's generated by XX and YY 2-qubit rotations on only nearest neighbor qubits. And this is really important, otherwise it doesn't work. Together with single qubit Z rotations, which can be on any qubit. And these two things sort of form the match gate group, which was originally introduced by Valiant and then connected to the theory of non-interacting fermions by Terhal and DiVincenzo, and I think a really interesting paper. And we are going to make our own little sort of addition to this, which is we're going to add discrete X flips to this gate set. So it's sort of a partially continuous, partially discrete gate set. But we only have to do this on one single qubit. So it's sort of an almost, it's a homeopathic addition to your gate set. But it lifts, this is going to make sort of the randomization properties of match gates quite a lot better, which is quite useful. And it's, so match gates are notoriously classically simulable. And it turns out that the orthogonal match gates, so adding these bit flips, does not destroy your classical simulability. So this is still a classically simulable gate set, which is useful for randomized benchmarking because you have to be able to compute these inverses. And it turns out that this is mathematically, it's a spin representation of the orthogonal group on 2n dimensions, where n is the number of qubits. And with that gate set, we can just do, naive randomized benchmarking, which is sample random elements, which is essentially sampling random matrices from O to N, which you can do efficiently, applying them in this sort of XXYY version, so applying them as match gates to some initial state, then computing the inverse, which you can do classically, doing this whole thing, and then doing this for different sequence lengths. And it turns out that if you do this, by this sort of central dogma from before, you get data that is precisely describable by a linear combination of 2n+1 exponential decays. And this is not the worst, but it's kind of bad. which is, I think, one of the reasons no one has sort of done it before, is because this is utterly unfittable for more than a few n's. So how are we going to fix this? Well, we're going to, in the vein of the previous paper, we're going to define these nice correlation functions, which depend on your sequence that you implement, and then we're just going to integrate away together with this function. And because of this sort of representation theory magic, it turns out that you can isolate these single exponentials. Note that we sort of, by a little tweak of the definition of these functions, we actually get rid of computing the inverse. So you don't have to explicitly implement the inverse. You sort of implement it implicitly, classically in this function, which is kind of neat. It makes the experiment rather much easier to do. The problem here is now we have something that's easy to fit, but it's not so clear that this thing can be estimated, especially since we don't want to estimate, we don't want to measure in a 3-design POVM because that's kind of hard. We just want to measure in the computational basis. And this function here, this f of x, there's a thingy missing here. This is generically a big function. It grows exponentially with n and k, which is sort of bad. So you can't sort of naively bound the behavior of this estimator. So you have to do a little bit more work, and we do this by explicitly bounding the variance of this estimator by just writing it down and then doing a lot of work. And what it turns out that it explicitly depends on is these really interesting sort of moment integrals over O to n, and UQ is here the spin representation, so it's sort of the match gates associated to this. And then overlapped with the n qubit 0 state. And we also do this for some other states, but this is sort of the general case, to the power 2t. So this looks a lot like a Weingarten function if this thing was an arbitrary unitary instead of a match gate. And it turns out that proving a polynomial bound on this variance, and hence on the sample complexity, hinges on you being able to upper bound this integral by a really small number, like this inverse exponential in n and t. And you can do this through some, really fun representation theory of O to n, which I go in a fair amount of detail in the main talk. So if you're interested in that, you should definitely check it out. But the key point is that this is possible. You can actually do this. It all works out nicely, but it takes a little bit of sweat to work out, to go through the mathematics. And of course, being good theorists, we went to Matt, who is an experimentalist and who helped us actually implement this protocol in a quantum computer to sort of test this match gate protocol to really check the quality of some gates on a real chip. And we did this. We implemented 2-qubit match gate benchmarking on the Rigetti Aspen 8 chip, which has a bunch more qubits, but we are only using 2. And by our previous rule, this has 5 exponential decays. So you really need this sort of splitting of exponentials to fit this properly. And we're sort of composing these match gates out of the interactions that are possible in this chip. And you can do this, and it works out kind of perfectly. Works really nice. We can estimate all of these parameters, and then we can average them out to sort of give an average match gate fidelity of 0.88, which is consistent with earlier experiments that people have done, which is nice because it means that nothing funky is happening, and B, it also means that you can really sort of trust this protocol as an experimental tool, and you can sort of use it in your toolkit if you're interested in these kind of things. All right, that was it. Thanks for listening.
Thank you, Jonas, for the very nice talk. I'm sure there should be questions by now from the audience after listening to 2 consecutive talks. Oh, indeed. So there's a question by Senrei Chen. He says, in the first talk, you mentioned that the general post-processing scheme for randomized benchmarking can be related to shadow tomography. Could you elaborate on this point?
That's actually a good question. And I don't really know the answer on this. We're sort of actively researching it at this point. The reason I mentioned shadow tomography is because the scalability happens for the same reason. So if you do shadow tomography in the sort of version that came out in a Huang Preskill paper at the end of last year. There they prove that with random Cliffords, you can estimate sort of any type of observable as long as the Hilbert-Schmidt norm of this observable is bounded. And the critical part of this proof is precisely a 3 design condition on the Clifford group. So somehow the effective measurement that they do is a state 3 design. And the reason it then works is because you can sort of invoke Weingarten calculus, and there's a bunch of dimensional factors that really neatly cancel. And our proof works for exactly the same reason. And this probably means that these protocols are in some sense equivalent, because they're both essentially randomized measurements over a sort of a 3 design. But I haven't really given it an incredibly large amount of thought.
Thanks, Jonas, for the answer. Are there any more questions that the audience may have? Well, if not, you can always ask Jonas offline. And with that, I guess we have come to the end of this morning session, and I'd like to thank all of the speakers of this session and the audience for attending. Thank you very much. Have a nice day.
Hi, everyone. Bill, hey, how are you?
Hi, Scott. How are you? Great to see you.
Good to see you too. Are you in Chicago?
I'm in Berkeley, actually.
Ah, all right.
Yeah. Yeah, so it's pretty early here.
Yes, indeed. All right. I'm honored that you would get up for this talk.
My pleasure. Okay, I think we'll be on in like about 10, 13 minutes.
All right. I'll just go get.
I'll give you an introduction and then you can get started.
Yeah. Oh. You're gonna be my host. Okay. I hadn't even.
Yeah.
Okay. Awesome. Great. So just to check, the talk is 50 minutes.
Yeah, I think that's right.
Okay, and is that including questions?
That I'm not sure about.
Okay.
I think so.
All right. Well, I'll do my best then.
Yeah. Okay. Including questions.
questions. All right. So let me try to do like 45 minutes then. Should I try sharing my screen or should we wait?
Why not? It's fine for,
All right.
fine for me.
It says I cannot start screen share while the other participant is. Well, why don't we
Okay.
just wait? You know, I mean, this particular thing I've never had a problem with. Like every other technical thing, I have had problems with. You know?
Right.
Okay. No, you know, I mean, as long as the screen sharing is enabled for me, then I'm confident that it's going to work. Yeah. So Stacy, Anna, Anne, good morning, or say Chiro, okay, and lots of new names, new faces. Hi everyone, good morning, or good evening, or good afternoon. Thanks for coming.
Oh, maybe you can try the screen share.
Oh, you want me to? Okay.
Yeah. Why not?
All right. Here, you see that?
Yeah, I do. That looks great.
All right. Good.
Okay, great. We'll be on in, I think, 1 minute, Scott. I'll give you a
All right.
brief introduction.
Yeah.
And then you'll start.
Great.
Okay, great. So let's get started. I'm honored to be able to introduce Scott Aronson, who will give the last invited talk of the conference. Scott is, of course, a leader in the field of quantum computation, an inspiration to all of us. He's not only a great researcher who has had many seminal results in the field, he's also a great mentor to us in the next generation of quantum complexity theorists. So today he'll tell us about BQP after 28 years. Please, Scott.
All right. Well, thank you so much, Bill. And it's an honor to be here to see so many familiar faces, including Bill himself, who I mentored when he was an undergrad. And so many new faces as well. It was wonderful to visit Riga in person in 2007. Spend time with Andras Ambayanis. And it's good to be back in Riga, even just virtually. So I want to tell you about BQP after 28 years. So this is an unapologetically retro talk, right? It's not about quantum supremacy directly. It's not about NISC or anything like that. But it's what I felt like I would most enjoy talking about, and hopefully I'll be able to say a few new things. So just to remind everyone, BQP is, arguably the central object of study of quantum computing theory. It was defined by Bernstein and Vazirani in their seminal paper of 1993 as bounded error quantum polynomial time, the class of languages for which there is an efficient quantum algorithm, that solves them with bounded error. And ever since, for 28 years, we've been trying to figure out how big is that class, right? What does it contain? How does it fit in with classical complexity classes? Now, when I think about BQP, I tend to have, one of two pictures in my head. One of them is, where it fits with just, P and NP, the two most famous complexity classes, and with the NP complete problems. And, our picture, I would say, since Shor's algorithm, has been that, BQP, seems to be this weird blob. I draw it with a wavy border because, everything quantum is spooky and mysterious, of course. But, it contains a few problems like factoring and discrete log that we don't know to be in P. But we don't expect BQP to contain all of NP, right? So we think of it as stopping short of the NP complete problems, most likely, grabbing some things in the no man's land between P and NP complete. And on the other side, we don't know whether BQP is contained in NP, right? It might, quantum computers might be able to efficiently solve problems for which classical computers can't even efficiently verify the answers, let alone finding them. Okay. In a little more detail, the best lower and upper bounds that we have on BQP have been pretty much the same since the late 90s. I mean, we know that BQP contains BPP, which is, classical bounded error probabilistic polynomial time. We know that BQP is contained in P to the sharp P. Okay, so, counting problems. Or more refined than that, it's contained in PP. Probabilistic algorithms with unbounded error. And even a little more refined, it's contained in this funny class called AWPP, which I won't bother defining. Let's see, in their seminal paper of 94, Bennett, Bernstein, Broussard, and Vazirani, BBBV, showed that BQP is self-low, meaning, BQP to the BQP, or, quantum algorithms with oracles for quantum algorithms are no more powerful than just ordinary quantum algorithms. That's a very important closure property of quantum algorithms. Fortnow and Rogers showed that PP to the BQP equals PP. Okay, so now some of you might remember a theorem I proved in 2004, which says that PP is also equal to post-BQP. That is the set of problems solvable by quantum computers with post-selection, with post-selected measurements. And once you remember that PP equals post-BQP, then it's kind of immediate why this theorem by Fortnow and Rogers has to be true. Okay. So, there are many profound questions about BQP, that were clearly on the agenda even in the early 1990s, and that have remained open to this day. Okay, so just to list, maybe the three most obvious ones, is BQP equal to BPP? Can quantum computers solve any decision problems efficiently that classical computers cannot? Secondly, is NP contained in BQP? Can quantum computers solve NP complete problems in polynomial time? And thirdly, what is an upper bound on BQP? Is it contained in NP? Or if not, then at least in AM. Or if not, then at least in the polynomial hierarchy. Okay, and one can ask many, many more arcane questions about BQP that are also open. One amusing example was asked by Lance Fortnow, in a blog post in 2005. He asked, "Is NP with a BQP oracle simulatable by BQP with an NP oracle?" Okay, so can you switch the order of these two seemingly incomparable computational models in this way? We'll actually return to this question later. It turns out to be interesting. Okay, but formally, we can speculate about these questions, but in terms of proving things, often there's not much more that we can do than just point out some relatively obvious relationships among some of the questions. One example that I kind of like is it is unlikely that both quantum computers can solve NP-complete problems in polynomial time, that is NP is in BQP, and also that BQP is contained in AM, because if both of them are true, then the polynomial hierarchy would collapse, right? Why is that? Well, just because BQP is closed under complement. So if BQP contains NP, then it also contains co-NP. That would mean that co-NP was contained in AM, which is known to imply a collapse of the polynomial hierarchy to the second level. Okay, so we can make some little observations like that, but what's kind of frustrating is that if we you could say that the closest thing we had to BQP before quantum computing came along was BPP, was probabilistic polynomial time, right? And for BPP, we are able to say a lot more than this. Okay, so just to remind you of some of the many things that are known about BPP, we know that BPP is contained in the second level of the polynomial hierarchy. That is the Sipser-Laudeman theorem from the early 1980s. Sorry, Sipser-Gatch-Laudeman theorem. Okay, so in particular, that means that the P versus BPP question is connected to the P versus NP question, right? If P equals NP, then the polynomial hierarchy comes crashing down, and then P would equal BPP as well, right? We don't know anything similar about BQP. Okay, we know that BPP can be simulated by polynomial size circuits. This is by non-uniform polynomial time algorithms. Okay, that is Edelman's theorem. BPP is in P/poly. Okay, again, we know no such thing about BQP. We know that if there was a polynomial time randomized algorithm for NP-complete problems, if NP is in BPP, then the entire polynomial hierarchy is in BPP as well. And in fact, the polynomial hierarchy would collapse. Okay, these are like homework exercises to prove these things, and we know nothing analogous about BQP. Now, all of these facts that I mentioned, they sort of all depend on the same trick. And the trick is a really simple one, that whenever you have a randomized algorithm, you can think about it as just a deterministic algorithm that receives a random string as an auxiliary input. Okay, so you always have this picture in mind that you can pull the randomness out of a randomized algorithm, right? Just think of it as a Turing machine, an ordinary one that just accepts, in addition to its input X, a random string R, and then you can play games like using hash functions to try to approximately count the number of R's that make the cause M to accept, and all kinds of stuff like that. Okay, that's what all of these theorems are based on. Now, as simple as that sounds, nothing analogous seems to be possible for quantum algorithms, right? What does it mean to pull the quantumness out of a quantum algorithm, right? Sometimes we are able to dequantize a quantum algorithm, but there seems to be no syntactic way to just, average over the different quantumnesses or something. I mean, randomness just seems to be baked in to the quantum computational model itself, or, rather it only appears at the very end, because of the Born rule, right? Rather than appearing at the beginning, the way that it does with classical randomized algorithms. Now, this difference between randomized algorithms and quantum algorithms has been absolutely crucial in many results in quantum complexity theory. And one example has been, the analysis of sampling-based quantum supremacy experiments. Okay, so for example, the work that Alex Arkhipov and I did on boson sampling a decade ago, the independent work that Bremner, Joza, and Shepard did on commuting Hamiltonians, right? It was all based on the idea that, well, you can, pull the randomness out of a classical randomized sampling algorithm, but you can't pull, you can't pull the quantumness out of a quantum algorithm, right? And so you can solve, you can sample certain distributions with a quantum computer, where if you had an efficient classical simulation for them, then you could then estimate certain sharp P complete quantities in BPP to the NP, and then that would collapse the polynomial hierarchy. Okay, but it's all based on this distinction. Okay, but you might wonder, how could we ever prove any of these distinctions between BPP and BQP? After all, we can't even prove today that BPP and BQP don't simply coincide, right? That they don't just collapse entirely. All right, well, I like to say that just like perturbation theory is, for my physicist friends, right? Relativization is for us complexity theorists. Okay, so relativization means, looking at questions relative to oracles. Okay, it is our way to prove things even when it is too hard to prove things. Okay, it is our way of getting some first intuitions about a question by just seeing, does the statement we're interested in hold relative to all oracles? Okay, or is there some oracle relative to which it's false? Okay, we know that that doesn't always tell us the truth about what happens in the real world, right? With IP equals P space being a very famous counterexample. Okay, but you could argue that if we can't even answer the relativized question, then that provides an obvious place to start, an obvious way to get a toehold on the thing that we are interested in. Okay, so what do we know about BQP relative to oracles? Well, quite a lot, actually. You could argue that the majority of what we know about BQP actually can be phrased or is best phrased in the black box setting. So, this goes all the way back to the beginning. Bernstein and Vazirani in their seminal paper, one of the things they did is they showed for the first time that there is an oracle relative to which BQP is strictly larger than BPP. Okay, so that was based on an artificial problem, recursive Fourier sampling, and the separation that they showed was only quasi-polynomial, but that was improved shortly afterward by Simon to an exponential oracle separation, of course, by inventing Simon's algorithm. Simon's algorithm shortly thereafter inspired Shor's algorithm. The heart of Shor's algorithm is period finding, which provides another exponential, or actually super exponential separation between quantum and randomized query complexity, and hence another oracle separation between BPP and BQP. Okay, now another seminal early result was from BBBV, who showed that there is an oracle relative to which NP is not contained in BQP. Or in other words, if there is a polynomial time quantum algorithm for NP complete problems, then it will need to be non-black box, just like a classical algorithm would need to be. Okay, and in effect, what they did is they proved that Grover's algorithm is optimal for the unordered search problem. And amusingly, they did that even before Grover's algorithm had been discovered to exist. Okay, now a maybe lesser known Oracle result is the one by Fortnow and Rogers. They showed that there are oracles relative to which P equals BQP, and yet the polynomial hierarchy is infinite. Okay, so in other words, they're saying that, well, you know, if you wanted to show that like P equals BQP would collapse the polynomial hierarchy, you know, which a priori might be a plausible thing to try to show, well, any proof of that implication would have to be non-relativizing, right? It could not work relative to all oracles. Now, you know, they heavily exploited that, you know, that we're only talking about precision problems. But a few years ago, Li Ji Chen and I were able to improve their result. We showed that there are even oracles relative to which every distribution that quantum computers can approximately sample can also be approximately sampled by classical computers. And yet still the polynomial hierarchy is infinite. Okay, now the word approximate was actually crucial to what I just said. Okay, and the reason is if every distribution that a quantum computer could sample could be exactly sampled efficiently by a classical computer, then that would collapse the polynomial hierarchy, okay? And it would collapse it in a relativizing way. In fact, that is exactly what Alex Arkhipov and I showed using boson sampling, and what Bremner, Joza, and Shepard showed using commuting Hamiltonians. Okay, so in effect, we've shown that any approximate analog of the basic theorems that we proved about quantum supremacy will have to be non-relativizing, which, you know, partly explains, I think, why it's been so difficult to do that. Okay, now Bernstein and Vazirani, well, at least as folklore, you know, around 93, and then Watrous in writing in 2000, show that there are even oracles relative to which BQP is outside of NP, and even BQP is outside of MA, Merlin Arthur. We could take the complement of Simon's problem as a good example of that. Okay, but then you could ask, well, why not go slightly further? Why not an oracle relative to which BQP is not in AM, for example? Or you know, hell, why not where it's not in the entire polynomial hierarchy? Well, these were, you know, notorious open problems for 25 years. Okay, I worked on them. You know, many other people worked on them, and we just could not get beyond MA. Okay, so in 2009, I did propose a candidate problem for separating BQP from the polynomial hierarchy. That was called the forrelation problem. Just to review what it is, forrelation is a problem where you're given black box access to two Boolean functions, f and g, and now you're promised that one of two things is true about how f and g were chosen. Okay, possibility one, they're just completely uniformly random Boolean functions and completely independent from each other. Okay, possibility two is independently they are uniformly random, but they are correlated with each other in a special way. That G is correlated with the Boolean Fourier transform of f, which with f hat, or equivalently, f is correlated with the Boolean Fourier transform of g, with g hat. Okay, I called this property being correlated. Okay, so you're just trying to detect whether these two otherwise random functions are correlated or uncorrelated. Okay, so I observed that this correlation problem is sort of maximally easy for quantum computers. It can be solved using only one quantum query to f and g. I conjectured, however, that not only did this problem require exponentially many queries to solve with a classical computer, which is something that I could prove, you know, which is maybe not that surprising, but that it was not even in the polynomial hierarchy. Okay, no pH algorithm can detect whether f and g are correlated or uncorrelated. This conjecture was finally proven just a few years ago in the breakthrough work by Ron Raz and Avishai Tal. They did, they worked on this for 4 years, and they did an amazing analysis of the Fourier spectra of AC0 circuits, that has lots of new implications for circuit lower bounds and pseudo randomness, but in particular, it implies that there is an oracle relative to which BQP is not in the polynomial hierarchy. Okay, in fact, they proved something stronger than that. They showed that any pH machine can solve the problem, guess whether F and G are correlated with or uncorrelated with only exponentially small bias. Okay, and we'll actually need that additional fact in the remainder of this talk. Okay, so what I want to do in the rest of this talk is I want to share some not yet published, work in progress with 2 students, William Kretschmer and Devon Ingram. Okay, that we've been stuff we've been doing over the last few years. The first question that we looked at was, building on the breakthrough by Raz and Tal, are there other long-standing open problems about BQP relative to oracles that could be picked off? Okay, and we realized, there were some low-hanging fruits, that could indeed be picked. For example, not hard to use Raz and Tal to show that there is an oracle relative to which BQP is not in NP/poly. Okay, or maybe more interesting, there is an oracle relative to which P equals NP, and yet neither is equal to BQP. Okay, so P can equal NP, and yet quantum computing can still be non-useless. Okay, at least in some oracle world. Right, this I don't know if that's relevant to any funding agency. Okay, but the idea for proving that oracle result, is you first use you use an oracle that encodes the correlation problem, and then let's say for every k, for every positive integer k, we recursively encode into our oracle, let's call it A, the answers to all the possible queries that NP machines could make to the oracle as it currently stands. Okay, but we encode in the kth iteration, we encode the answers to those queries using strings of length n to the k, so that weaker machines couldn't even see the answers. Okay, and if we do that in that staggered way, then we can, relative to our oracle, we can make P equal to NP, equal to the polynomial hierarchy. Okay, and the key question is, well, why have we not then also made P equal to BQP again? Okay, and the reason why we haven't is because of Raz and Tal's theorem. Okay, because even with queries that encompass the whole polynomial hierarchy, we still can't solve those correlation instances. Okay. So now let me move on to some more interesting results that we can show by building on Raz and Tal. Okay, so here's the first one. We can construct an oracle relative to which P equals NP, and yet BQP equals P to the sharp P. Okay, so and they're not equal to each other. Okay, so we can make NP ridiculously weak, and we can make BQP ridiculously strong at the same time. Okay, so you could think of BQP will just not let its aspirations be constrained by NPs, right? And this is very unlike what happens with BPP, right? We said before that if P equals NP, then it also equals BPP. Okay, and then BPP is quite weak. Okay, so how do we do that? Well, the idea is we first use, let's say, some exponential sized instances of the majority problem, and that is known to make the pH different from P to the sharp P. Right? This is just circuit lower bounds for AC0 that were known since the 1980s, right? That AC0 cannot solve majority. Okay. Next, again, we're going to do one of these staggered constructions where, like, for each positive integer k, using strings of size n to the k, we're going to take our oracle, let's call the oracle A, and we're going to encode into the oracle the answers to all possible NP queries, that can query the previously constructed parts of the oracle. And we're also going to encode into our oracle the answers to all possible Sharp-P queries that query the previously constructed part of the oracle. But crucially, we are going to hide the answers to the Sharp-P queries inside of correlation instances. Okay, so in other words, if you want to know the answer to some Sharp-P to the A, query, you can get that from, by going to a further out part of the oracle. But in order to get it, you have to solve a bunch of exponentially large instances of the correlation problem. Let's say, each instance, the answer to each instance revealing one of the bits that you want. And so what we do this way is that we've made P equal to NP relative to this oracle, because by just the same trick of recursively encoding the answers to all the NP queries. We've also made BQP equal to P to the Sharp-P. Okay, why have we done that? Well, because a quantum algorithm can just solve the correlation instances and thereby get the answers to all the Sharp-P queries. Okay, but now we can use Rosenthal to say that we did not recollapse pH with P to the Sharp-P. Okay, intuitively, because if you're pH and you want to solve these Sharp-P instances, well, they're hidden inside of these correlation instances. Okay, and to you, the polynomial hierarchy, the correlation instances are just indistinguishable from completely random, uniformly random, exponentially long strings. Okay, so you don't even get an exponentially small advantage in guessing the answers to them. Okay, so that's the intuition. Let me tell you about another new result that we can get. We can show that there exists an oracle relative to which NP is contained in BQP, but yet the polynomial hierarchy is infinite. Okay, so in other words, what we're saying is that if there, you might dream of showing, you might dream of getting evidence that there is no fast quantum algorithm for NP complete problems that would say, that if NP is in BQP, then that would collapse the polynomial hierarchy. Okay, but we're saying that if that is true, it can only be true for a non-relativizing reason, right? Relative to all oracles, NP could be in BQP without it having any effect on the polynomial hierarchy. Okay, and again, this is very different from what happens with BPP, right? If NP is in BPP, that does collapse the polynomial hierarchy. Okay, so how do we construct this oracle? All right, well, our first step will be to use a random oracle. Okay, and by a breakthrough rather recently by Rossmann and Cervedio and Tan, we know that a random oracle will actually make the polynomial hierarchy infinite with probability 1. Okay, we don't strictly need Rossmann, Cervedio, Tan, but it makes our lives a little bit easier. Okay, so use a random oracle, make the polynomial hierarchy infinite, and then we take our oracle and we encode into it the answers to all the possible NP queries that query the previously constructed parts of the oracle. But once again, we hide the answers to those queries inside of exponentially large instances of the correlation problem. Okay, now by doing that, we put NP into BQP relative to our oracle, right? So we have revealed the answers to all the NP queries, but in a way where a quantum computer can access them by solving the correlation instances. Okay, but once again, by Rosenthal plus a suitable hybrid argument, right? These correlation instances still look uniformly random to a polynomial hierarchy machine. Okay, so, and because they are indistinguishable by pH from just uniformly random oracles, we can then apply the result by Rossmann and Servetio and Tan, which says that as far as pH is concerned, this is just a random oracle. A random oracle, is going to make pH infinite, is not going to recollapse it. Okay, so that's what we do. Now, we wanted to, do some more acrobatics with BQP, as it were, right? But to go further, we needed more than just Rosenthal's achievement by itself. We needed more than correlation, which is a positive result, for quantum computing, a powerful thing that quantum computing can do. We also needed some information about what quantum computers cannot do. Okay, now, since the 1980s, a central tool for oracle separations, for example, separating pH from p-space, has been the random restriction method. Okay, many people know the random restriction method as a central tool for circuit complexity, for circuit lower bounds. Not everyone knows that random restrictions were originally invented, as a tool for proving oracle separations. Okay, and so what we realized was that we needed a way to take random restriction arguments and make them mesh with quantum computing. Okay, we needed to integrate random restriction arguments, into quantum complexity theory. Okay, so we actually proved a random restriction lemma for quantum algorithms. Okay, for the acceptance probabilities of efficient quantum algorithms. Okay, which we can then use. We don't always need its full power. Okay, but let me just, the statement of it is a little bit technical, but let me try to walk through it. Okay, basically what it says is that, suppose I've got a quantum algorithm, call it Q, and suppose that Q makes a small number of queries to some Boolean input string, call it X. So so we have some n-bit input string X. Let's say, Q makes T queries to X. Okay, and then, we just fix some parameters, call them K and P. Okay, and then what we want to say is that the acceptance probability of Q will simplify nicely under random restriction. Or in other words, if I randomly restrict most of the bits of X to being, a 0 or 1, if I randomly restrict most of them to just be consistent with X, and then just let the other bits vary, right? Then with high probability, a quantum algorithm will not notice very well the bits that are still varying. Okay, so it says if we sample a set S, of indices, so that each index I is in S with independent probability P. Right? This is just the usual trick you do with random restrictions. Then with high probability over the choice of that S, there is going to be, within S, there might be some small set of influential variables, right? So yeah, there might be inside of S a small subset of indices that are actually kind of important, right? We call that L, right, of size at most K. But for every input Y that only differs from X on the bits of S that are not in L, the Q will not be very sensitive to toggling those bits. The probability that Q accepts X will be close to the probability that Q accepts any input Y that only differs from X on toggling those bits of S that are outside of L. Okay, and they're with the difference bounded by this quantity here. All right, so that was a bit of a mouthful, but when you try to prove this, it's really just a sort of a careful application of the original BBBV hybrid argument. Okay, in other words, what was originally used to prove the optimality of Grover's algorithm. right? You're really just using the fact that a quantum algorithm has only so much, query magnitude or query mass to spread among all of the different input bits. And so it can't spread it everywhere. And if I pick S randomly, then probably it has not gotten lucky enough to pick many indices within S to have queried with a large magnitude. Okay, so you could say, really this is just like a version of BBBV. All right, so let me give you an example application of sort of the combination of BBBV with random restriction, although not yet using sort of the full power of this lemma that we have. Okay, so we can show that for every k, there is an oracle relative to which the k plus first level of the polynomial hierarchy is not contained in BQP to the kth level of the polynomial hierarchy. Okay, so sigma 2 is not in BQP to the NP. Sigma 3 is not in BQP to the sigma 2, and so forth. In fact, better than that, a random oracle will achieve all of these separations with probability of 1. Okay, so this is kind of munging together the classic result that the or you could say as improved by Rossmann, Servetio, and Tan, that as we now know, the polynomial hierarchy is infinite relative to a random oracle with probability 1. Okay, we're saying that is still true even if you throw BQP into the mix. Okay, and really to prove this, you can just plug BBBV, into Rossmann, Servetio, and Tan's sort of random restriction argument. Right? You can't just use the statement of their result as a black box, but if you look at how the proof of their result works, then you can just kind of munge it together with BBBV. Okay, so now I can get to what is maybe our most interesting result. Okay, and this is something that I had wanted to do or had toyed with for a while. So we can show that for every k, there is an oracle relative to which BQP contains the kth level of the polynomial hierarchy, but does not contain the k plus first level. Okay, so if you would like BQP to contain the 17th level of pH, but not contain the 18th level, there is an oracle that will do that for you. Okay, we have that much control over how BQP relates to the polynomial hierarchy. So now, the idea for proving this is, well, first we're just going to use a random oracle, which by what I told you previously makes the k plus first level of the polynomial hierarchy be outside BQP to the kth level. Next, we're going to use the correlation problem, there it is again, in order to encode answers to all of the possible sigma k queries. Okay, so we're sort of, and that will put sigma k into BQP, right? So we sort of make the kth level of the hierarchy easy, but only for a quantum computer that is able to solve correlation. Okay, next we use Rosenthal to show that these sigma k machines cannot solve the correlation instances. In fact, they just look random to them. And because they can't solve them, because they look random, the sigma k machines cannot sort of recursively query the oracle about their own behavior. Okay, so in putting sigma k into BQP, this is the reason why we don't just automatically put sigma k plus 1 and sigma k plus 2 and so forth into BQP. And then the final step is to use Rossmann, Servetio, and Tan, right? Plus, use random restriction to show that then sigma k plus 1 is now still outside of BQP, which has now been collapsed with BQP to the sigma k. Okay, the polynomial hierarchy is still infinite in this setting. Okay, so so let me make a note about this. Now let's imagine that per Lance Fortnow's speculation of 2005, suppose that NP to the BQP was contained in BQP to the NP, okay? And imagine also that NP was in BQP, okay? So, with these crazy assumptions, what could we do? Well, we could take NP to the NP, and that would be an NP to the BQP, which by assumption would be in BQP to the NP, which by assumption would be in BQP to the BQP, which is just equal to BQP. So in other words, NP in BQP would imply sigma 2 in BQP, okay? But we've already shown that there is an oracle world where NP is in BQP, but sigma 2 is not in BQP. Okay, and what that means is that we have therefore also given an oracle world where NP to the BQP is not in BQP to the NP. Okay, and we have therefore solved Lance Fortnow's problem from 2005. At least, I mean, he asked for an oracle relative to which, this containment was not true. So we can now do that. Okay, and I also wanted to note that all of these oracle results are sort of only possible because of Rosenthal's breakthrough, right? And the way to see that is that if BQP were contained in AM, by some relativizing proof, let's say, then all of the statements that we've talked about would have been false, right? You can check that. Like if BQP were in AM, then NP in BQP would collapse the polynomial hierarchy, right? And so on and so on, right? So at the very least, to build the oracles that we've done here, you need to make BQP outside of AM, and that has only been possible since Rosenthal in 2018. All right, so let me just give one last application of our random restriction lemma. And this one really does require its full power, okay? So we can show, that there is an oracle relative to which PP, say, is not in BQP to the NP. Okay, so far, not very surprising, right? We already said that sigma 2 is not in BQP to the NP, but now we can go further, okay? We can say, relative to a suitable oracle, PP is even not in BQP to the NP, to the BQP, to the NP, and we can interleave them as often as you like, okay? Any constant number of times, I mean. But then, if you stare further at the statement of our random restriction lemma, it even works for QMA. Okay, so we can say that PP relative to some oracle, PP is outside of the QMA hierarchy. Okay, the QMA to the QMA to the QMA and so forth. Okay, in fact, we don't even care how large the witness is. Okay, all that matters is the number of queries that a quantum algorithm makes to the oracle in verifying the witness. Okay, which tells us even some quite absurd things. Like there is an oracle relative to which PP is not in MIP star to the MIP star to the MIP star and so forth. And yes, this is true even though in the real world, as we now know, MIP star is equal to RE, right? Can solve uncomputable problems. And yet, in oracle worlds, we can make MIP star to the MIP star to the MIP star, not contain PP. Okay, so that's, fun with oracles. Hey, likewise, we can make an oracle where P and NP and BQP and QMA all collapse with each other, and yet PP does not collapse with them. Okay, and we could contrast this with the classical case, right? PP is equal to post BQP, which we were saying it doesn't have to collapse just because QMA collapses. Okay, but in the classical case, if P equals NP, then P also equals post BPP, right? So this is yet another difference between quantum and classical. Okay, so to summarize, we've shown that relative to suitable oracles, we can almost completely unshackle BQP from the complexity classes around it, like the polynomial hierarchy. And we did so by exploiting just two facts about quantum computation. First of all, their ability to solve the correlation problem, which is not in PH by Rosenthal. And secondly, the inability of quantum computers to solve unordered search better than Grover. Okay, so and we could do all of these things even while BPP remained sort of shackled to the classical complexity classes. Okay, so there are lots of interesting problems that we didn't solve. I would love to have an oracle where P equals NP, but BQP goes all the way up to X, or hell, why not NX? Non-deterministic exponential time. I would love to have an oracle where QMA was not in BQP to the NP. We don't know how to do that. And then, our random restriction lemma is probably, is very plausibly much weaker than what is actually true. And, if you got a stronger random restriction lemma for BQP, then maybe it would imply, much stronger oracle separations, or, at the very least, quantitatively stronger ones. Okay, but, now I know that people, for some reason, are curious about the real world, the world with no oracles. So I'll end by sharing my speculations about the real world, or the things that I would bet money on. Okay, I would bet that P equals BPP and that neither of them is equal to BQP. That quantum computing is genuinely stronger, at least for some problems. I would bet that NP is not contained in BQP, that we're not going to solve all, NP complete problems efficiently with quantum computers. Now, as for BQP contained in NP, I would not bet money either way about the real world, to be perfectly honest. Note that under de-randomization, it would be enough if BQP were contained in AM, right? And if it is, then it would also be contained in NP. And, so what do we know, right? It comes down to questions like, is there any explicit instantiation of the correlation problem that wouldn't require an oracle? Or is there a decision version of boson sampling, which sort of is in BQP and is not in the polynomial hierarchy, most likely, but which is not a decision problem, which is a sampling problem. So, is there, can you modify these things? I don't have a good intuition about it. Okay, so that's it. And thank you for listening, and I'm happy to take any questions.
All right, great. Thanks, Scott, for an awesome talk.
Thanks.
So we have, time for maybe one or two questions.
There's a question in the Q&A here. Let me end the share. Q&A. What is my intuition for why P equals BPP? It is not equal to BQP. Well, I'm not going to say anything that will shock anyone here, right? I mean, P equals BPP, because we know that follows as long as there are good pseudo-random generators, right? And that in turn follows as long as some very plausible circuit lower bounds are true. And we've known that for 20 plus years, right? And then as for BQP, well, it's just, if you want to believe that BPP equals BQP, then you've got to believe that factoring and discrete log are in BPP, which, look, I don't have an excellent intuition that they aren't, but, it's not just, one or two problems that would have to generalize to sort of every problem involving hidden structures in abelian groups, right? And then, if you wanted, I think it's kind of hard to imagine that that BPP would equal BQP without also promise BQP being equal to promise BPP, right? But if promise BQP equals promise BPP, then that would mean that there is just an efficient classical algorithm to simulate arbitrary quantum circuits, or simulate quantum chemistry and so on, right? And there, we have like almost a century of physicists and chemists trying to solve these problems and only, being able to solve them in exponential time in the worst case. So I guess that would be what the case would rest on right now.
Okay, great. So I think we're finally out of time.
Okay.
So thanks a lot, Scott.
Sure.
We thank him again virtually.
All right.
And it looks like we're taking a break, and we'll be back in a few minutes. So thanks a lot.
Okay.
Right. Hi, Daniel.
Hi, Anna.
Are you ready to share the slides?
Yes, should I read?
Let's try doing that.
Okay, good.
Yep. Okay, I can see the slides. And I can hear you. Okay, so it's time to start the session. So welcome everyone to the first evening session, Latvian time. And our first speaker is Daniel Franke. He will speak about efficient learning of quantum extensive observables.
Thanks, Anna, for the introduction. I should say that the paper I'm talking about is on the archive today with a different title. So the archive title is Learning Quantum Many-Body Systems from a few copies. This is joint work with Computation. And this paper is about tomography or learning of quantum states. And we're in the setting where we're given access to some copies of an unknown state role on NQDITs. And we can do a single copy measurements on it. And then after doing some post-processing, we want to be able to obtain an estimate of the state and from that make predictions about it. Now, one of the important things when working in this is, of course, number of samples of the state that we need to accurately or faithfully get an approximation of it. And we also want to do this in a way that the post-processing is as efficient as possible, but this talk we're mostly focused on the sample complexity. And of course, these quantities all depend on what we consider a good recovery and what are the assumptions we actually make on the state. Because if we want to, for instance, get an epsilon approximation of an arbitrary state without any assumptions on it in trace distance, then we know that the number of copies actually increases exponentially with the system size. So we want to avoid this exponential scaling. And there are two ways of avoiding this. So the first relaxation is to focus on physically motivated states, because most of the states we have in the lab or care about, they have some underlying locality structure. So say they could be some Gibbs thermal or ground state of a local on a lattice or something of local Hamiltonian on a lattice. So in this presentation, we will depart from the assumption that we know that our state is indeed some Gibbs state and have some upper bound on the inverse temperature on some known locality structure encoded into these operators EI. And in this setting, it is known that you can actually learn such a state with a number of samples that grows polynomially with system size. So another natural assumption is to also relax the observables we care about. So again, most of the observables you're actually interested in also have some underlying locality assumption. So for instance, we could consider an observable O, which is just a sum of OIs, such that these OIs all act only on subsystems, let's say of size L squared. So for instance, in this case, L by L blocks. And in this case, the expectation value of such an observable only depends, of course, on the reduced density matrices on each block. And if you only care about observables like that one, then with the framework of, for instance, classical shadows, you can learn all such expectation numbers with a number of samples that only grows logarithmically in system size and exponentially in the locality of the underlying observables. And you don't have to make any assumptions on the state whatsoever. So in summary, if we assume that we have a local Gibbs state or some sort of locality structure for the states we want to recover, then we can get away with polynomially many samples in system size. Whereas if we then make the assumption that we only care about k-local observables, then we can get away with logarithmically many samples in system size and a scaling that is exponential in the locality. And in light of this, it is natural to ask whether we can combine the assumptions of both protocols and get the best out of them. And in this work, this is exactly what we achieve. So we identify a third condition, namely that the underlying state satisfies a so-called transportation cost inequality. And combining the transportation cost inequality with shadows and many-body tomography methods, namely the maximum entropy principle, we can then learn all k local observables with a number of samples that grows polynomially in system size, logarithmically in system size, and polynomially on the locality of the observables we actually want to learn, somehow getting the best of these two protocols. Now, how do we do that? I mentioned this transportation cost inequality. What is that? Well, first, I quickly need to define what the Lipschitz constant of an observable is. Unfortunately, the talk in which this concept is defined will take place in the next session. I think De Palma will talk about this. But roughly speaking, this is the quantity of an observable that quantifies how stable it is to local perturbations, say. And it turns out that if for local observables like this one, this Lipschitz constant is very small compared to the operator norm, because, well, clearly, if you have an observable of this form, if you only perturb a small subsystem, the expectation value cannot change a lot. So operators with small Lipschitz constant are somehow capture well local observables, and then in analogy with the trace distance, we can ask how well two states are distinguishable by these Lipschitz observables, because this somehow quantifies better physical properties of the state in some sense. But then the next question is, how do we actually control this Wasserstein distance? And we do this in this work by using these transportation entropy inequalities, which say that for a given state, this Wasserstein distance is upper bounded by the relative entropy, which is a much simpler object to control. And then one can combine this inequality with maximum entropy methods and classical shadows to actually get the result I claimed before. And we have some examples of states that satisfy the requirements for our results to hold, but we conjecture that all Gibbs states at high enough temperature, even with long-range interactions, satisfy our assumptions. And with that, I would like to finish the summary and be happy to take any questions.
All right, thank you very much, Daniel. If anybody has any questions, please type them into the Q&A tab or raise a hand and we will unmute you. All right, looks like there are no questions right now for Daniel. Okay. All right, thank you very much, Daniel, again.
Thanks.
And let's switch
then.
with the next one. So yes, please unshare. And Armanda, would you like to try to share on screen?
Yes,
Hi.
sure. So can you see both my screen and the pointer, right?
Yes, yes, everything is good.
And the pointer too, right?
Yes, and the pointer too, yes. Okay, we'll wait just one more minute and we'll start. right, so let's get started. The second talk is given by Armanda Kuntval about single-shot error correction of 3D homological product codes.
Thanks, Anna. So this is a joint work with Michael Wasmer, Yoskarov, and Earl Campbell. You can find the long talk on YouTube or the paper on the web. So I will, oh no, okay. So the very broad problem we wanted to address in this work is what if we assume that syndrome measurements can be noisy. So the syndrome, which is the information we need in order to perform error correction in the error correction code picture, is noisy too. So to understand what I'm talking about here, I will refer to the 2D Ising model, where we put qubit on faces and stabilizers on edges. So for instance, we can put Z stabilizers on all the edges, and if a bit flip error occurs on this gray qubit highlighted here, what we know is that the syndrome that is going to lit up as a consequence of this error is given by all the stabilizer that lies on the border of this qubit. So it's here highlighted in red. And this works for all errors on the system. But what we want to take into account is that a bit flip error can occur during the measurement step. So what we actually see instead of the nice red border of the gray region is something like this. So here we can see that there is a line of syndrome that is wrong, and this loop is open. And in this model, in the 2D Ising model, what we find is that actually all the correct syndrome correspond to closed loops. So we, thanks to this feature of the syndrome in this setting, we can perform single-shot error correction, meaning that even if we have one round of noisy measurement, like this one, we are able, like for instance, using a minimum weight perfect matching decoder to first correct the syndrome and then find the correct recovery operator for the correct syndrome. So this is what single-shot error correction means. And our question was, is there a sufficient criterion in general for codes that is able to assure us that the code has a single-shot property? And to this end, we propose the concept of confinement. So again, referring to the 2D Ising model, we can observe that there exists a relationship between the error weight, which is the gray region here, and the syndrome, which is the perimeter of this area. So this is a feature that can be generalized, and we gave it a go with this definition that basically say that a code has confinement if for all error of small weight, upper bounded by some constant that increase with the code size, there exists a function of the weight of the syndrome for which this relationship holds. So we say that a code has confinement if we are able to upper bound the weight of the error in this way. Previous definition of confinement has been proposed, but before, the only function that was allowed was a linear function. Here instead, we allowed the function f, the confinement function of the code, to be any polynomial. So we can have quadratic confinement function or cubic confinement function and any function. What we have been able to prove is that, yes, confinement is a sufficient criterion for a code to exhibit a single-shot property in the adversarial noise setting. So we are able, if a code has confinement and we assume that our error model is adversarial, both on the qubit and on the syndrome, then we are able to keep the error on the system under control over time using just one round of noisy measurement. More to this, we have been able to prove that if the confinement function is linear, then the code family has a single-shot threshold. And this is quite relevant because, for instance, expander codes have linear confinement. So we find again another result that was already known. But what is maybe more interesting is that we do believe that confinement can be sufficient in general, like also cubic confinement or whatever confinement function, to as a sufficient criteria for a code family to exhibit a single shot threshold. So what we have conjectured is actually that there is something more that here is highlighted in yellow of codes that have confinement that is not linear, but is anyway enough for these codes to be resilient to stochastic noise errors, both on the syndrome and on the qubit. And to investigate our conjecture, we have proved that a well-known class of codes, the 3D homological product codes, has cubic confinement. And for instance, the 3D toric code is an example of codes in this class. And we have investigated their behavior under stochastic noise, both on the syndrome and on the qubit numerically. So we have implemented a two-stage decoder. For the 3D toric code, we have used at first stage minimum weight perfect matching to correct the syndrome, and then belief propagation with order statistic decoding for the qubit errors. And our results are the best up to date. So in the case of noise-free syndrome, so if we suppose that syndrome measurements are perfect, our threshold approaches the optimal bound given by the statistical phase transition. And in the single shot mode, we beat the sweep decoder and find a threshold of around 2.9%. So what has been good of our decoder is that the class of 3D homological product codes doesn't comprehend only topological codes, but various LDPC codes. And we have also implemented a version where we use belief propagation plus OST for both stage. And again, we find confirmation of our conjecture, and we found a threshold of around 2.7%. So to sum up, there are still some questions that I would like to be answered sooner or later. So whether confinement is sufficient for a single shot threshold. So we have the result that linear confinement is, but we do believe that confinement in general is, even if we have not been able to prove it. And then, of course, whether this is also a necessary condition, because it's nice to have both ways. And yes, last, maybe is a bit out of the scope of my talk, which is what's the relationship between confinement and macroscopic energy barrier. So I'm happy to take questions or also answers to my questions. Thanks.
All right, thank you very much, Armando. Yeah, it would be nice to answer some of the questions, right?
Yeah.
Okay, so are there any questions? Okay, I see a question from 10. 1 second. Yes, you are unmuted.
Can you hear me, Anna?
Yes.
Great. Hi, everybody. So I'm afraid I don't have an answer to any of those three questions, but I was going to ask, have you explored the 4D case? Because I guess that would be the natural place to look next for further evidence for this conjecture.
Yes. So I have cheated a bit because 3D homological product codes have a confinement and a threshold just for one of the two kinds of error. And yes, to do this, we used like the meta check structure. So that, and if you have a 4D structure, then we have meta check for both stabilizers. So also 4D codes have, yes, have soundness. So that's entails that they have confinement. So I'm quite confident that like belief propagation can work and will give a threshold. But again, it's not linear. So, or at least I have not been linear, able to prove that the confinement function is linear. So my proof will not work.
I was going to ask, do you know what the confinement function is for the 4D case?
I think the proof can work the same with the cubic function, because you can treat the two things separately, or maybe you go to fourth. Like is a bit of. I think the cubic function for the 3D homological product codes could be improved. So it would not be more than 4, like power of 4, but.
Thanks, Amanda.
Thank you.
All right, thank you so much. And we are out of time. Could you please unshare the screen? Yes, perfect. And Simon, could you please try sharing the screen? Yes.
Yeah.
Okay, perfect. I can see your screen. All right, and our next talk is by Simon Borton about limitations on transversal gates for hypergraph product codes.
Hello, everyone. Yeah, I had a lot of fun working on this problem with Dan last year. It was one of those things that, like, it was an idea that was born in an afternoon. And I could straight away see that something was happening. And then it took a couple of months to really nail down all the phenomenon. So yeah, I'm really fascinated by this fundamental problem of quantum computing, which is we need to protect our quantum state, but not too much, because we also want to manipulate it and perform computation. And so these two goals of protection and manipulation they butt up against each other. And there's a lot of results in the literature that say you can't have too much of one without destroying the other one. And so the result that I'm talking about today is one of those results. And this is one of the best ideas we have for protecting quantum states, is to encode into a quantum code, like a stabilizer code. And then to manipulate the state, we look for these transversal gates, which are single qubit unitary operators. And because it's just a tensor product of these guys, hopefully it's fault tolerant if we do it well enough. Each operator isn't going to spread around errors too much. The main result of the paper is that these hypergraph product codes, and there's some fine print here which I won't talk about, they have the transversal gates, if any, are at best restricted to the Clifford group. And the ingredients come from, it's a bit of a throwaway remark that Brave and Koenig make in their 2013 paper. It's not the main result of their paper. It's just a kind of a motivating example. And the idea is that if you look at a generic logical operator of your code, if you look at the region, if you find a region that contains a generic logical operator for your code, and you separate that from another region such that the intersection is correctable on these two red regions, then transversal gates must be Clifford gates. That's kind of a magical result, which I still find mysterious. So that's how this proof in this paper works that I'm talking about today. Let me just try to motivate what these hypergraph product codes are. They're generalizations of the surface code. So let me just do the surface code, but I'm going to assume you're all geniuses and you can see immediately how this generalizes that. So what I've got here is a repetition code. That's the parity check matrix. And I think of this as like an Ising model. This picture here is a kind of an Ising model. And we take another one of these repetition codes, and this hypergraph product is a kind of a tensor product, and this is what it ends up looking like. It's the service code, and we can start putting down errors, and the qubits live on the edges of this code, and the check operators, there's these blue check operators that detect Z-type errors, and there's these green check operators on the faces that detect X-type errors. And let me bring up the Bravy-Koenig argument. Let's see how this works. I'm going to just put down a logical Z operator here and a logical X operator here. And so that's going to be my gamma. Okay, whoops, I did this wrong. Put the X operator on the bottom here. By the way, I'm showing off my little service code app. Okay, so that's the gamma region. And now let me try and spell out what the delta region looks like. We'll put another Z operator over here and an X operator along the top. And the intersection of these two operators is just this qubit down in the bottom right corner and this qubit up in the top left corner. So that's the red regions on the right here. And those qubits don't have any logical operators. You cannot fit a logical operator there. So the argument in the paper generalizes exactly this to more general classical codes A and B. Going to just wrap it up there if anyone has any questions.
All right, thank you very much, Simon. Any questions in the Q&A, or just raise your hand and we will unmute you.
Yeah, I guess I have another picture, which is, let's see if I can do this. This is showing some of the structure of the logical operators in general for a more general A and B here. You get these much fatter regions that you have to deal with. I get so confused talking about this stuff, so I'm not even going to try and explain it all right now. I'm just going to assume everyone is a total genius and immediately understands it.
All right, I don't see any questions as of this moment, so thank you very much, Simon, again. All right, Nicholas.
Hi.
Hi.
Let me just share my screen real quick.
Let's see. Yep, I can see your screen.
Very good. Yeah, let me know when I can go.
Yeah, let's just wait 2 minutes
Sure.
so we're on schedule. All right, let's get started. So the next talk is by Nicholas Bergman about balanced product quantum codes.
Thanks very much, Anna, and thanks very much to the organizers. So today I will talk about joint work that I did with Jens Eberhard this year. So this talk deals with LDPC quantum codes. So just a quick reminder what those are. LDPC quantum codes are a special type of codes where each check operator acts on a constant number of qubits, and each qubit participates in a constant number of checks. And this is a very large class of quantum codes, and all your favorite codes probably belong to this class. So for example, all topological codes belong to this class. Compared to what's known in the classical world, we know that we can get LDPC codes which are good. And good has a very strict definition. Good means that the number of encoded qubits scales linearly with the number of physical bits or qubits, and the distance, meaning like the measure for how many errors we can correct, also scales linearly in the number of bits or qubits. And a big open question is, can quantum LDPC codes be good? This is far from being resolved. And actually, until recently, it wasn't even clear whether we can have codes with distance scaling beyond some polylog n times square root of n. So something that kind of, I know, significantly violates even the simple surface or toric code. And there has been some advances recently. So first of all, Hastings-O'Donnell had a breakthrough result with their fiber bundle code construction, where they showed that they can achieve distances scaling with n to the 3/5 up to polylog factors. And this was followed by Panteleev and Kalachev, who kind of showed that there's a parameter, so they can kind of achieve almost linear distance. And then we followed up a week later with our balanced product construction, and we just have like a slight improvement on the parameters of Hastings-O'Donnell. The difference for us is that the first two examples are random, whereas our construction is explicit. So we can actually give a guarantee that our parameters are bounded this way, rather than having this be true with high probability only. So in Amanda's and Simon's talks, you have already seen these type of product constructions, which these are all special cases of. So the simplest one is this hypergraph or tensor product, where we just take two classical codes and we obtain a quantum code. And the idea roughly of Hastings-O'Donnell was to introduce twists, and this increases the distance. So in the most trivial case, you can imagine we just kind of, I know, twist torus, enforcing a detour of the logical operators. But they took this idea to the extreme. So they take a random code with random twists, and they show that the distance scales n to the 3/5 with high probability. And our starting point was to see whether we can do this explicitly or without any randomness. And I won't be able to kind of go through the exact definition of balanced product quantum codes, unfortunately. But just to kind of give you a rough intuition, the idea is that we have two classical codes and a symmetry group acting on both. And one way of viewing our construction is to take the tensor product of these two classical codes and then perform a symmetry reduction using the symmetry group. And this gives us our balanced product quantum code. So the properties that we obtain are as follows. So first of all, the number of logicals scales as n to the 2/3. The z distance scales linearly, and the x distance scales as a third root of n. And I want to mention that actually we use Panteleev and Kalachev's bounds, which kind of slightly improve on the number of logicals here. Yeah, by taking another product, we obtain our final result. I should have also mentioned that this is just one example of this construction, and it's just like an example where we can prove these properties. So the balanced product construction itself is a very general tool. And I should also mention that it is likely, or it's possible that beta bounds are attainable. So you saw in the Panteleev and Kalachev work, there was this parameter that you can have tune, where there's a trade-off between k and d. But for this, we need finite groups with certain properties, and we are not aware of any finite groups of these properties. So in our case, we actually use a group called the projective general linear group. And we tried other groups, but actually they give worse distances, but more qubits. Just to give you a concrete example and some geometric intuition for the experts, the idea is that we have classical codes which kind of come equipped with a hyperbolic Riemann surface. And the idea is that we take this Riemann surface and we kind of, wrap it around itself and then kind of glue in repetition codes, meaning cycles. And in one particular example where we have some genus 14 surface with an order 13 cyclic symmetry, which kind of goes all over the surface, we obtain a quantum code which has 500 physical qubits and code 6 logical qubits. And we can do some Monte Carlo to upper bound the distances. And actually the X distance we believe we can believe this is tight. So for the X distance, actually this is kind of expected. The check weights are not too high. So this is just to kind of show you that these are not completely crazy constructions, but certainly they're not planar. One additional thing which makes balance products different from the previous fiber bundle and lifted products is that they are symmetric. So fiber bundle and lifted products are kind of defined in terms of something which kind of plays the role of a base and one which plays the role of a fiber. So this is terminology loaned from differential geometry. But there's some asymmetry is what I want to say. And there are some restrictions of what the fiber can actually be in the lifted product case. On the other hand, the balanced products, they kind of give you a different point of view, and the product is symmetric in its input factors. And this leads us to a conjecture that I want to mention. So we conjecture that it's possible to build good LDPC quantum codes using balanced products. The idea is we take two suitable classical codes and a common symmetry group, which has a certain size. And then we conjecture that the balance product between the two is a good LDPC quantum code. And we've already checked that they actually already have linear encoding rate. So all that's left is proving the linear distance. Yeah, just to kind of summarize, balance product codes are a powerful tool to explicitly construct quantum codes with good parameters. We can kind of, I know there are lots of examples that I didn't mention that we could kind of investigate. They're similar to other twisted products, but they're not random, and they're symmetric, which leads to our conjecture. And that's all I had to say. Thank you very much.
Thank you very much, Nicholas. Are there any questions? Doesn't look like there are any questions.
Sharing.
Thank you. Oscar, would you like to try sharing the screen?
Sure.
I can see your screen.
My screen.
Yes. Okay, let's just wait a minute or two. Okay, let's get started. So our last speaker of this session is Oscar Higgett, and he will talk about subsystem codes with high threshold by gauge fixing and reduced qubit overhead.
Thank you. I'd like to thank the organizers for organizing the conference. So yeah, this talk is about some joint work with Nico Breukman at UCL. And so yeah, the motivation is, can we beat the surface code? And the surface code is the focus of many efforts to build a fault-tolerant quantum computer. And that's thanks to having 4 qubit measurements and a good threshold of around 1% for circuit level noise. But there are many challenges remaining, some of which are the fact that it has a very large overhead, requiring around sort of 1,000 physical qubits per logical qubit for many use cases. The weight for checks can be too large when you take account for kind of crosstalk in some devices. And the threshold still isn't high enough for experiments. So I'd like to see if we can get the threshold to improve the threshold as well. And so we try and kind of address these challenges in the work. One aspect of it is that we introduced a new family of quantum operating codes, and we showed that this family of codes has a 4.3 times lower overhead than the surface codes when you take into account circuit level noise, and it also has weight-3 checks. And we also introduced a new technique for decoding subsystem codes, which is a broad family of quantum operating codes, and so that results in some high thresholds, especially under bias noise models, and it's also widely applicable to many families of subsystem codes. A quick recap on subsystem codes. They're stabilizer codes where you just choose not to store quantum information in some subsets of the logical qubits. And these qubits that you don't use, they're the gauge qubits. And the operators that act on them are gauge operators. And then in some subsystem codes, you can write the stabilizers as a product of some low weight gauge operators, and then measure each gauge operator individually, and then multiply the results to obtain the measurement of the stabilizer. And then some gauge operators, it's worth noting that the gauge operators themselves, because they don't mutually commute, each individual outcome can be randomized, but the product is fixed. An important subsystem code, which was introduced in 2013, is the subsystem surface code, shown in this diagram. So the yellow circles here are data qubits, and each blue triangle is a Z gauge operator, and then each red triangle is an X gauge operator. And then you take the product of the 2 Z gauge operators in a face to form a 6 qubit Z stabilizer, and then you take the product of the 2 X gauge operators in a face to form an X stabilizer. We generalize this to hyperbolic tessellations. And so here we've got now a subsystem code where the checks are still weight 3, but the stabilizers are now weight 12. So we take the product of 4 X gauge operators in a face to form an X stabilizer, and then likewise for the Z gauge operators. We've also got an improved encoding rate. So there's a finite encoding rate, and that's a consequence of the hyperbolic tessellation that we use. And then, so in the subsystem toric code, you can kind of construct a schedule using kind of translational invariants. I'm just going to construct a schedule for some sort of 1 square of the lattice. You can't do that for the hyperbolic tessellations, but we show that you can use a symmetry group to construct a very efficient measurement schedule to read out the gauge operators sort of with an ancilla in a circuit of CNOT gates. The performance of the code, so we simulate the performance under circuit level depolarizing noise and looking at encoding 338 logical qubits. And so then this is where the 4.3 times reduction comes from. So we find that around this regime of 0.1 to 0.2% circuit level depolarizing noise, all else fixed, we're using around 4 times fewer physical qubits with the subsystem semi-hyperbolic codes compared to the rotated surface code. And then the new technique is schedule-induced gauge fixing. So the idea here is to repeat the gauge operator measurements. So although the gauge operators don't mutually commute, the ones of different types don't mutually commute, operators of the same type do trivially commute. And so if you repeat a gauge operator measurement, then you can temporarily fix it as a stabilizer. So going up in time here, these kind of circles represent the measurements of the gauge operators and stabilizers. And so when you repeat the gauge operator measurements, you can just temporarily fix them as stabilizers, which improves the decoding performance. And this is especially useful under bias noise models. So for example, if you've got Z bias, then you can fix the X gauge operators more often. So you end up with sort of having weight 3 checks and stabilizers for many time steps. And that's good for handling Z bias. And so if as an upper bound, if you only ever measure the X checks for Z bias, then we get a threshold of 2.2%. So that's sort of a 4 times improvement in the threshold compared to if you just use the subsystem target code as you previously would have done just with standard schedule. So it's useful and we also find an improvement for depolarizing noise, but it's more pronounced for bias noise. And so in summary, so there are these 2 different parts of the paper. There we look at the subsystem hyperbolic codes that we introduce, and so these have an encoding rate of a 6 and weight 3 checks. And then the first example of a code that outperforms the surface code under circuit level depolarizing noise, reducing the overhead by a factor of 4. And we've also introduced this schedule-induced gauge fixing technique. So it's all in software. You don't have to change the hardware implementation. And we show that it can increase the threshold of the subsystem target code for depolarizing noise, and then even more so for bias noise. And it's quite general, so you can just kind of apply the technique to wide families of subsystem codes, although we only simulated these, the subsystem toric and hyperbolic codes in the paper. And yeah, on that note, thank you for listening and happy to take any questions.
All right, thank you very much, Oscar. Are there any questions? If there are any questions, again, please type them in Q&A tab or raise a hand and we will unmute you. All right, looks like there are no questions at the moment. Thank you again, Oscar, and thank you for all the speakers of this session. The next session will start in 28 minutes. All right, hi Vishal. Would you like to try share screen? Yeah, okay, very good. It works.
I just want to go into presentation mode. Can you still see my slides?
Yes.
Okay, perfect.
Yeah, very good. Okay, so let's get started. Welcome everyone to the second evening session by the conference Latvian Time. Our first speaker is Vishal Kataria, who will speak about RLD, Fisher Information Bound, for multi-parameter estimation of quantum channels. Go ahead.
Thank you, Anna, for the introduction, and thanks everyone for coming to my talk. As Anna said, this talk is about RLD Fisher information and its application to estimating quantum channels. This is joint work done with my PhD advisor, Mark Wilde, and I'm a PhD student at Louisiana State University. For more details, you can obviously go to our longer pre-recorded talk that's on the TQC website, or also to our archive paper. I'll keep things brief since I don't have too much time. And in most of these cases, everything is explained better in the longer talk. So quickly to introduce the setting and the problem that we focus on. The problem we focus on is estimating a number of unknown parameters that's encoded in a quantum channel that goes from A to B. What we want to do is to estimate these parameters. We generally consider D parameters. We want to estimate them simultaneously while minimizing the total error of that estimate, which we quantify in a specific way, which will be introduced in the next few slides. The setting is what's known as the sequential or the adaptive setting of estimation, which is where if we're given n uses of this unknown channel n, then we apply them in sequence one after the other. We're allowed to have entanglement between the AB systems and reference systems. And finally, we also have these interleaving channels that are given by the S1, S2 through to Sn-1. And in this case, we finally do a measurement because the ultimate goal is to obtain a classical estimate of these parameters. So theta itself is basically a vector of D variables, and theta hat at the end will be a vector of D real numbers, which captures the estimates of these strategies. This figure essentially captures the most general way to process to do any sort of information processing on n uses of a quantum channel. One specific subcase of this sequential setting is what's called the parallel setting, which is a different sort of intuitive way to easily process n uses of a channel, where instead of having them happening one after the other, the n uses of the channel happen at the same time. However, there can be a larger entangled state. But parallel strategies are contained in this set. So this is truly the most general setting in which to process n channels. I'll go straight to the RLD Fisher information. In this case, we're estimating D parameters. So it's a D cross D matrix. Just to back up, instead of channels, we consider, let's say, quantum states. The quantum states are parameterized again by the same parameters. Then the D cross D matrix has the following matrix elements that's given in equation 1. It can also be defined using what's called the RLD operators, which is totally equivalent to this. I'm just not doing it here because for lack of time. What we want is something called a Kramer-Rao bound, which is a lower bound of the form of equation or inequality 3. A Kramer-Rao bound is really the fundamental operational quantity in estimation theory. It provides fundamental lower bounds or limits on the precision that any estimator can take. As I said in the previous slide, the RLD Fisher information in this case is a matrix, and we are interested in scalar bounds. To get scalar bounds, we introduce a weight matrix W, and we define in equation 2 something called the RLD Fisher information value. This is really the fundamental quantity that we will work with henceforth, even extending it to quantum channels. And for quantum states, this inequality in 3 has been well known, and it's just the scalar Kramer-Rao bound for state estimation. So for quantum channels, as you know, a quantum channel is a dynamical object. It's not a quantum state. So whenever we're invoking the definition of a state quantity for quantum channels, we have to optimize over the input state of that channel. That's exactly what's happening in equation 4. And that's how we define the RLD Fisher information value of a channel family. Now that we've defined this, what we're aiming for is a lower bound similar to the one for quantum states. So we're aiming for the lower bound on this, you can call it the weighted covariance matrix, where W is, as we defined earlier, that positive semi-definite matrix with unit trace. What is interesting or unique about the way we go about it is that we want a bound that holds for n-round sequential estimation rather than just parallel estimation. So in general, if I just go back to this figure, that means that that bound can involve, or that estimation strategy can not only involve the input state, but also all of the n-1 interleaving channels. And that's exactly what I've written here. However, our bound, which I'm going to show now, has a number of nice properties. It holds for the sequential estimation protocol of the form inequality 6 here. And you can see that it has a certain n dependence, where this is what's known as the short noise limit or the standard quantum limit sometimes. And it also uses the RLD Fisher information value of quantum channels that was defined a couple of slides ago. This bound has a number of nice properties. First of all, I did say that it holds for an n-use sequential protocol. However, it's single letter. And as you can see in the inequalities right-hand side, the quantity involved only involves a single use of the quantum channel. That is, the quantity to be computed as the lower bound involves an optimization of a single channel use rather than of n channel uses. I'll go into this in a little more detail in the next 2 slides. The other 2 nice properties are that it can be solved via an STP, which is obviously a good thing. And because it's single letter, this means it can be calculated for a number of problems of interest. And lastly, just repeating that it applies universally, that is, it applies to all quantum dynamics, that is all quantum channels, and also it applies in the case of sequential estimation strategies, which also subsumes the parallel case, as I mentioned earlier. I'll quickly talk about why it's single letter, and just the way I'm going to do it is just by stating our main technical result really, which is this chain rule for RLD Fisher information. And what does this chain rule mean? It essentially means, I'll try to explain it using the figure again. It means that a catalyst state that's input to the channel cannot increase the RLD Fisher information by more than the channel's RLD Fisher information. And again, I'm doing a very quick job of this, but if you go to our extended talk or to our paper, this is explained better. It essentially implies that for each, there's no super additivity, so to speak, of this RLD Fisher information across channel uses. And that's why the RLD Fisher information of an n-round sequential strategy is just n times that of a single use estimation strategy. And that's basically what gives us the single letter nature of our bound. So I've just hit 8 minutes. So I'll stop here and thank you. If you have any questions, I'll be happy to answer.
All right, thank you very much, Vishal. Are there any questions in the Q&A tab, or you can raise a hand and we will unmute you. All right, looks like there are no questions at the moment.
Okay.
Thank you again, Vishal. All right, Giacomo, would you like to share the screen?
Okay, sure.
Perfect.
Hey, you see the slides?
Yes. Yes, very good. Okay, so our next speaker is Giacomo De Palma, and he will talk about the quantum Wasserstein distance of order 1.
So, hi everybody. First of all, I would like to thank the organizers of this conference to give me the opportunity of this talk, where in these 8 minutes, I will present our recent proposal of quantum generalization of the Hamming distance. And this is a work in collaboration with Milad Marvian, that now is at the University of New Mexico, Dario Trevisan from the University of Pisa, and Seth Lloyd from MIT. And it has been recently published on the IEEE Transactions, and this is the journal reference. Okay, let me start with some motivations for this work. So most of you will probably be quite familiar with the Hamming distance between bit strings that counts the number of different bits. And you will know that this, the Hamming distance, it's ubiquitous in several fields like classical probability, information theory, and also machine learning. And then, since like qubits are the quantum version of bits, it will be kind of natural to have a version of the Hamming distance for qubits. But before this work, actually this quantum generalization of the Hamming distance was not there. And actually the property that the Hamming distance captures is that a flip of a single bit is a small change with respect to the Hamming distance, because it changes by only 1. But still, it can generate, like in the quantum setting, if you flip the state of a qubit, you can generate a state orthogonal to the initial state. And actually, all the usually employed distances for quantum states, like the Hamming distance, are unitarily invariant, and then any couples of orthogonal states are maximally far, and they do not capture this property that touching a single qubit is a small change. So let me come to our definition of the Wasserstein distance of order 1. We start by defining a notion of neighboring states. So 2 quantum states of n qubits are neighboring if they coincide after discarding 1 qubit. So after we trace out the state of that qubit. And like we know that for the Hamming distance, if we touch a single bit, the distance can change by at most 1. And then we require that each couple of neighboring states must have distance at most 1. And then we require that this new distance is induced by a norm on the set of quantum states. And there is this, it is possible to prove that the set of norms on the set of density matrices that assign distance at most 1 to any couple of neighboring states actually has a maximum. And we are then done because we define such maximum norm as the quantum Wasserstein norm of order 1. And the induced distance on a set of states will be the quantum Wasserstein distance of order 1 on the quantum states of n qubits. And a nice property of these definitions is that this Wasserstein norm and Wasserstein distance can be computed via a semi-definite program, so such that we can have efficient classical algorithms to compute the value of this distance. Okay, so we have a new distance. Let's look at its properties. So first, this distance actually recovers the Hamming distance for the quantum states of the canonical basis. So it is actually a quantum generalization of the Hamming distance. The second property is that this distance behaves like an extensive quantity, in the sense that if we partition our n qubits into subsets A and B, we can prove that the distance between the 2 arbitrary global quantum states rho and sigma is lower bounded by the distance between the marginals on A plus the distance between the marginals on B. The third fundamental property of this distance is the robustness with respect to local quantum circuits, and in particular, any quantum circuit can expand this distance by at most the size of the light cones of the input qubits. And the last and probably most important property of this distance is a continuity bound for the von Neumann entropy of the quantum states. And this continuity bound, okay, I will not write the precise expression because it's not very informative, but the fundamental thing that this bound implies is that we can guarantee that two states will have a difference in the entropy that grows smaller than the number of qubits n, if the distance between these two states grows slower than n over log n. And actually, we have to say that we are not really sure that this log factor has to be there. It may just be an artifact of our proof. Okay, so let me conclude with the perspectives on how this distance can be employed. Like a first field of application is quantum machine learning. And we have already applied it in the framework of the generative adversarial networks that roughly have the goal to train a quantum circuit to reproduce a given quantum state of which we have some copies available. And here the place where this distance kicks in is as a cost function or quality factor to measure like the distance between the exact state that we want to reproduce and the state that is actually generated by our circuit. And you can find more about this in this paper on the archive. Then still in the context of quantum machine learning, this distance can be employed to like quantify the robustness of some quantum machine learning algorithm that acts on a quantum input by exactly measuring the size of a perturbation in the input. And then another application is the field of concentration inequalities. So this framework can be employed to prove some concentration inequalities for local quantum observables for roughly Gibbs states of local Hamiltonians at high temperatures. And you can find more about this in this paper that's just a few days ago appeared on the archive. Then the robustness with respect to shallow quantum circuits can be employed to explore the computational capabilities of these circuits. And as other two final applications, we know that the Hamming distance plays a key role in the design of classical codes for error correction, and we expect this quantum distance to play a similar role in quantum error correction. And then finally, in the setting of quantum communication, this distance can be applied in quantum rate distortion theory, where the goal is to transmit a quantum state with some distortion allowed in the recovery. And this distance will play the role to measure the quality of the recovered state. So this is all I wanted to tell you. Thanks for the attention. I'm ready for questions. I see there is something.
All right, thank you very much, Giacomo.
Hey.
Any questions? All right, looks like there are no questions at the moment. Okay, so let's switch the speakers. And Marcus, hi, are you ready to share the screen?
Yes. So, can you see my screen? Okay.
Yes, I can see your screen.
Okay, great. So.
Okay, just one more second. Okay, Very good. Okay, so the next talk is by Marcus Hasenor, and he will talk about the interaction-free channel discrimination.
So thank you very much for the kind introduction. I will talk about interaction-free channel discrimination, and this work is joint work with my PhD supervisor, Michael Wolf, and you can find the full version on the archive under this number. Okay, interaction-free channel discrimination is the combination of two things, interaction-free measurements and quantum channel discrimination. Interaction-free measurements were introduced in 1993 by Elisur and Weidmann via their bomb tester experiment. And this thought experiment goes as follows. So suppose you have a box and you know that inside of this box, there's either nothing or an ultra-sensitive bomb. Now, by an ultra-sensitive bomb, I mean a bomb that is so sensitive to light that even if only a single photon hits that bomb, then this bomb will explode. Now, our task is to find out whether there's indeed a bomb in the box or not, without letting the bomb explode. So classically, if photons were classical particles, then this would seem to be at least an impossible task, because either you send a photon through and then the bomb will explode, or you don't get any information. But in 1993, Elisur and Weidmann proposed to put this box into one arm of a Mach-Sender interferometer. So I have drawn here this Mach-Sender interferometer. Mach-Sender interferometer consists of two 50-50 beam splitters and mirrors, and here we have photon detectors at the output, and we insert a photon here in the lower path. And what I've drawn here is these two cases where there is a bomb in the box, where there is a bomb in the box and where there is no bomb in the box. Okay, and one can analyze this proposal via introducing, one way to analyze this proposal is by introducing two quantities, namely the error probability, which is the probability that if you measure in the end and then you have to guess whether there was a bomb in the box or not, that in that case that you guess wrongly, right? So this is here, can be analyzed to be 12.5%. And then there is this other probability, which is the interaction probability, namely, which is the probability that if there is a bomb in the box and you apply this setup here, that the bomb will explode. Okay, so this was 1993 by Elisur and Weidmann, and in 1995, Kwiat et al. Analyzed the multi-use version of this. So instead of using this, probing the bomb or the box only once, you are now allowed to probe the box many times, and you have this more generalized version where you can probe the box n times. Okay, and in the end, you still measure. Now, the crucial point here of this is that the bomb here acts as a measurement device. And if you have many, many measurements once in a row, and then you only rotate by a slight angle with these beam splitters, this is what they do with the state, then what you get is the quantum Zeno effect. And this indeed, the analysis of this protocol leads to quantum Zeno effect mathematics. And what the analysis of this such a proposal shows is that the error probability, as we had before, goes to 0 as 1 over n squared, where n is the number of times we use the box, and that the interaction probability also goes to 0 with 1 over n. So this means that in this asymptotic case, we can really tell with probability approaching certainty, approaching 1, whether there is a bomb in the box or not, while simultaneously ensuring that the bomb will not explode. Okay, now what we tried to do is to generalize this by asking what other kinds of objects can we discriminate in such an interaction-free way. And to this end, we looked at this proposal as a quantum channel discrimination problem. So here we have one channel which describes the bomb, and then we have the identity channel which describes no bomb. Okay, as we have seen before, the quantum general protocol for probing things is given by a sequential scheme like this, where T is now the unknown channel and where we intercept with several quantum channels that are under our control. And then in the end, if we apply such a protocol, then in the end we get some state which we can measure, and this state depends on the unknown channel, and depending on our measurement outcome, we can then guess which thing was actually in the box. And
we might go wrong with this guess, so we obtain some quantity, namely the error probability. Okay, now this is classical channel discrimination. Now, what does it mean to be interaction free, or what does it mean that the bomb does not explode? So for this to make sense, we need to assume, or we assume in analogy to the bomb tester experiment, that there's such a thing as a vacuum state, which means that there's a state such that if I send this state through the box, then whatever is in the box, nothing happens to the interior of the box. Okay, and if you have such a state, then you can define the interaction probability in an operational way. Namely, you look at the channel in this open system picture where this V now is the Steinspring dilation of this channel T. And basically, you imagine a daemon sitting in the box who has access to the conjugate channel and whose task is now to figure out if during the execution of this protocol, there was ever a state different from the vacuum state applied to one of these inputs of the channel. And if he finds out that this was indeed the case, then he says this is an interaction. And then you can define a probability, which is the probability that he finds out that such a thing, that we sent something other than the vacuum through. Okay, good. And what our results is, we basically analyzed this proposal. And what we found is a necessary and sufficient criterion for when this interaction-free channel discrimination is possible, meaning that the interaction probability and the error probability go to zero simultaneously. To state this result, we need one more small concept, which is very much related to the concept of a decoherence-free subspace, namely that some channel T is isometric on V, on some subspace V. If we restrict that channel to operators on that subspace, then it looks like an isometric conjugation. Okay, and with this concept, we can state our main theorem, namely that two channels TA and TB can be discriminated in an interaction-free manner if and only if there exists such a subspace, such that at least one of these two channels is isometric on V, and this V contains the vacuum, and the channels do not agree, so they're not the same, if we restrict them to operators that act only on that subspace. Okay, and this theorem is the combination of two things: a protocol which does the job in case these conditions are satisfied, and we propose a protocol which has some nice properties. First, it works uniformly, which means that if we fix the channel TA, and we don't know what TB is, but we just know that this TB satisfies one of these conditions, then we can still find out whether the channel in the box, or whether the box is channel TA or some other channel, TB. Okay, and also we find that this interaction probability goes to zero as 1 over n with an increasing number of channel uses n. And we also find, modulo some technicalities, that this this decay rate of 1 over n is the best achievable one for this task. Okay, and finally, we prove that it's not possible if these conditions are not satisfied. And for that case, we simply prove some inequality which quantifies the trade-off between the interaction probability and the error probability. And with that, I will finish my overview talk, and I'm happy to answer some questions.
All right, thank you very much, Marcus. Are there any questions? And again, you can type the questions in Q&A tab or raise a hand to be unmuted. All right, looks like there are no questions. Thank you very much, Marcus, again. And Min, are you ready to share the screen?
Yes, give me a second. Can you see my screen?
Yes. Okay.
I cannot turn on my video though, but that's okay. Hi everyone, my name is Ming Chan. I'm from University of Maryland, and today I'm going to talk about a scheme to protect digital quantum simulation against the violation of symmetry. This is a joint work with Juan Su, Dan Kani, and Jake Taylor. So the aim of digital quantum simulation is to simulate the dynamics of a quantum system on a quantum computer. For example, if we have some interacting spins described by a Hamiltonian, then we're going to map these spins onto qubits on a quantum computer, and then use quantum gates to approximate the dynamics of the system. The approximation of the dynamics by these quantum gates, they introduce some error that in the best case, they just deviate the simulation from the ideal evolution. So if you have a good quantum simulation algorithms, that is a good way to break this time evolution into these quantum gates, then the simulation will be very close to the ideal evolution. And this small incorrect, small error is not a big problem. But in some cases, these errors, they may violate the symmetry of the system that you're trying to simulate. And what happened in the end is that you end up with some state that cannot be described by your model. And those are unphysical states that we need to somehow get rid of. So here's a thought. Instead of letting the symmetry of the target system being violated by the error of the simulation, is there a way to use the information that this system has a symmetry to suppress the simulation error? And the answer is what we call a symmetry protected simulation. For this scheme to work, we need to assume that the Hamiltonian has a symmetry that is a set of unitaries that commute with the Hamiltonian. And then we assume that we're going to simulate the evolution using an algorithm that first breaks the evolution into many small time steps, and then approximate each time step using a quantum circuit. An example of such an algorithm would be trotterization, first order and then higher order trotterizations. And that's why we call a raw simulation, where we just repeat the same circuit many times. In what we call a symmetry protected simulation, we're going to insert the unitaries drawn from this symmetry S in between the steps of the simulation. The reason why we do this is because you can think of the circuit C delta T as the correct evolution plus some error due to the simulation algorithm. Because these unitaries UK, we draw them from the symmetry of the system, they commute with the correct part of the simulation, and they don't affect the correct part of the simulation. But the error, they may violate this symmetry, and they do not commute with these unitaries UK. And so we can try to use these unitaries UK to manipulate this error. And it's actually the part of the error that violate the symmetry. That's the part that we want to suppress here. So here's an intuition for why this scheme works. In a raw simulation, what happened is that every circuit C delta T will introduce some small error. And in the end, these errors, they add up to a large error at the end of the simulation. But in a symmetry protected simulation, these errors, they are rotated by these unitaries UK that we insert in between the step of the simulation. So these errors from each step, they are rotated in a way such that the total error, the error from different steps of the simulation, they may cancel each other out. And we end up with a smaller error at the end of the simulation. The main result of our paper is an error bound on is a bound on the error of a simulation protected by this symmetry. And in deriving this bound, we show an exponentially tighter bound for the quantum Zeno effect. It turns out that this unitree UK is very similar to a quantum kick in quantum control, where you just frequently kick a system by some unitrees. And these kicks, they will project the dynamics of the system onto the eigensubspace of the kicks. And here, what these unitrees UK, what they do is that they project the dynamics of the system onto the symmetry subspace. And we apply this symmetry protected scheme to simulate the dynamics of spin models. And in particular, we use a Heisenberg model to demonstrate how the scheme works and why the scaling with the number of shorter steps, how the scaling in different schemes. And we also apply our symmetry protected scheme to the simulation of lattice gauge field theories. And these are models where you have a lot of symmetries in the system. And we show that using the symmetry protection, we can suppress the leakage into the unphysical subspace due to the simulation error. We also show that sometimes these symmetry protection can also suppress experimental noise, especially the noise that are correlated between different steps of the simulations. So if you are interested, please check out our extended talk and also our paper here. And thank you for your attention.
Thank you very much, Min. Are there any questions? All right, looks like there are no questions at the moment.
Thank you for having me here.
Thank you, Min, again. All right, Sepper, would you like to try sharing the screen? Yes, I see your screen.
Hello.
Hi.
So is my screen visible?
Yes, I see your screen.
Yes.
Yep, very good. We're gonna wait 2-3 minutes until your time, just in case somebody wants to join. All right, Shepard, you ready?
Yes.
So our last speaker of the session is Sefer Nijami, and he will talk about the quantum gravity in the lab, interpretation by size, and traversable wormholes.
Thank you so much for the opportunity to speak here. I'm going to talk about quantum gravity in the lab and size winding, which is based on 2 papers written with Adam Brown, Hrant Karibian, Stefan Leichenauer, Henry Lin, Grant Sutton, Lenny Susskind, Brian Swingle, and Michael Walter. So because the extended talk is already online, I'm going to talk about more about high-level picture and motivations in this overview talk. And our motivation is basically, for this paper, our motivation is really twofold. We want to understand, we would like to understand the emergence of gravity and spacetime from quantum phenomena with the tools of quantum information science. And more importantly, we want to design NISQ near-term experiments that are relevant for quantum gravity. And our starting point is really the holography that taught us to think of gravity and spacetime as dual descriptions of some non-gravitational complex and chaotic quantum systems. In other words, you can have in your lab a complex Hamiltonian, you can prepare it. And if this Hamiltonian, and this in some cases, this Hamiltonian will have a gravitational dual in the sense that you can look at this different set of parameters and it would look like a quantum gravity with the space-time and the fluctuations of space-time and everything. And here we wish to simulate this non-gravitational dual, the Hamiltonian that could or could not correspond to a gravity in a gravity system through the holographic duality. I want to simulate it in the lab and detect the signatures of existence of the gravitational dual. The signature we use here for gravity is really a natural one, and that's the fact that things fall in gravity. And we really want to detect things falling in the dual picture of what you prepare in the lab. So here is a schematic picture. On the right is a schematic picture of what we do. And so if you look at these 2 thick orange lines, they're basically 2 points in the lab. So these are the points that you really prepare in the lab. And forget the middle part for a minute. So you have a 2-part system that you prepare in the lab. And what you do is that you insert a signal on the left system, and you let your system evolve, and it runs, your circuit runs. And if you have a gravitational dual, which will be a form of a space-time sheet between left and the right systems, your particle, the signal you inserted will fall through this gravitational space-time and will be received by the other subsystem of your experiment in the lab. So you would be able to receive a signal that is that virtually is falling in this gravitational spacetime. But if you don't have this gravitational dual, if your Hamiltonian doesn't have this spacetime associated with that, you will not be able to receive the signal. There is no reason to receive the signal because there is no way, there is no spacetime that it falls through and be received by the other boundary in your lab. So this is a good test of existence of gravitational dual. And in fact, it is kind of a fine test. For example, the many models of gravity with like random unitaries or random time evolutions that people use to model black holes, they will not work here. You really need to have a Hamiltonian with gravitational dual to see the signal. And the kind of interesting fact about this kind of experiments is that it's the quantum gravity science or technology behind this type of experiments is really developed in real time. So these are all really new concepts, phrase science from quantum gravity. And the space-time that we use here, this sheet of space-time between these 2 boundaries, is called a traversable wormhole, and was discovered in less than 5 years ago, I think. And so as a part of our experimental proposal, we take this schematic picture, this gravitational picture, and write down a precise quantum circuit that you would be able to run in the lab and detect and insert the signal and detect and receive the signal through this circuit. So this circuit is completely equivalent to this gravitational picture. And you can see that it's not a particularly complex circuit, but you have to, it requires a preparation of a thermophile double state, which is nothing but a purification of a thermal state. You have to time evolve backwards and forwards, and you would be able to insert your signal. And there is somehow a simple coupling, which is an exponential of a ZZ coupling, and you have to time evolve again. And if everything works fine, you receive the signal that you inserted here in this quantum channel, which corresponds to this point here at the other side of your quantum circuit. And and the Hamiltonian in the test is this HL that defines the time evolution as well as the thermal state. So if this HL has a gravitational dual, you expect to get a signal back for very low temperature thermophile double state. And so a goal here is to basically study this quantum circuit. And we see that this quantum circuit is actually teleports or sends signals in two different regimes. One regime is which we call, it's a second regime here is the gravitational one I was talking about. It can send many and a large number of qubits, and it works at very low temperature thermophile double states. But there is accidentally, it actually teleports in a different regime, which is very high temperature regime, and it only requires a scrambling dynamics. So this is easier to implement in the lab. It's easier to analyze. It looks like a complex version of an ordinary teleportation. And it's something that if your lab is, if you're in a lab, it's not powerful enough to do the gravitational experiment or low temperature thermophile double experiments, the simplest experiment will always test for scrambling. So this is what, and I'm going to talk about these two types of regimes a little bit in the next slides. So the first regime of teleportation, which I said is unexpected from gravity, works best for infinite temperature. So in thermophile double, instead of thermophile double, I said you can put bell pairs, and you can have any scrambling dynamics, and you see that you will get a signal almost perfectly well on the other side of the circuit. So it works. But it works in as I said, in distinct regime of gravity. So you can really distinguish whether it's gravitational or it is this kind of interesting teleportation. And it teleports only one qubit. And as I said, you can analytically solve this problem. For example, you see that even for 7 qubits and different realistic Hamiltonian models, you get very good signal which match your analytical results. The second regime of teleportation, which was really the interesting gravitational one, which was harder to understand, requires understanding a new notion. It works in a totally different mechanism, and this mechanism we call size winding. And for this type of teleportation to work, you really have to look at this particular operator, this time-evolved operator O of t times rho beta to the power of 1/2, where rho beta is a thermal state, and you expand it in the Pauli basis on all 4 to the n Pauli's basis of the space of all operators, and you look at these coefficients. So in the cases that you have gravitational dual, you will see that these CP coefficients will have a complex phase, and this phase is really linear with the size of your Pauli operator. The size means the number of non-identity single qubit Paulis that go there, the number of x's plus number of squared plus number of z's. So if this CP has a phase that is linear in the size of this Pauli operator, the expansion of this operator, we say that this Hamiltonian and this operator has a size winding property. And you will see that this leads to mathematically leads to the second regime of teleportation. It's harder to see and analyze in most quantum systems. And this explains the mechanism behind the gravitational teleportation, which is a bit more complex than other regimes of teleportation. And it works only for chaotic systems with holographic dual and near this rambling time. And we can test it for the SYK model. For that, I think I'm near the end of my time. So I thank you, and I wait for questions.
All right, thank you very much, Sepper. Are there any questions? So there is a question from anonymous attendee to the previous speaker, and Min will type the answer in the Q&A tab there. Are there any questions to Sepper? All right, looks like there are no questions. Thank you very much, Sepper. And thank you very much to all the speakers of this session. So right now, Andres Ambais would like to give a few words.
So thanks to all on behalf of the local organizers, thanks to all the speakers for attending this virtual QIP. I think we have heard a lot of great talks, and big thanks to all the speakers. Also, thanks to the program committee for putting together this great program, to steering committee for choosing the invited talks, and to the team of local organizers that made this possible. We had more than 10 local volunteers putting countless hours, and I would like to thank them all. And thanks to all of you for attending and listening. We had more than 465. We had 465 registered participants. So, Evgenis, could you put up the slide with the participant statistics? So 465 registered participants from 37 countries. I'm glad that you all attended. Thanks to everyone, and hope to see you in person in TQC 2022 in Urbana-Champaign, Illinois.